Good evening. Am I audible to all of you?
Yes, audible.
Yes, you are.
Sir, you are audible.
Yes, sir, you're audible.
Thank you. So, even before we start, I'll quickly make some announcements so that you can decide if you want to stay for the session or not, right? So, see, these are the important points I want you to know. So, the attendance is not, right. So, the workshop, after the workshop sessions end, sometime in February, there'll be an OPP and you have to clear the OPP. Only then will you be given a certificate, right? So that certificate that you will receive is entirely based on your performance in OPP, right? That's the first point, and we will not take into account your attendance for these 3 sessions, right? So 4 sessions. So that is something that I want to inform upfront. And these sessions are being streamed. Okay, so each one of these 4 sessions, they will be streamed and the links will be available on YouTube, right? I'll make them available to you. So all of them will be added to this particular link that you see here, right? So tiny.cc/mlt_workshop. So that is the place where all the collabs will be there. And I'll also make the links to these sessions available there. You'll also find previous terms links here. Okay, so all of this will be available. So in case you want to watch this session offline, meaning at your own convenience later in the day or sometime later this week, that is fine, right? So it's not necessary that you have to be in this particular session. Okay, so why I am saying this is we have noticed in the past that at least this is what I guess happens. So students join into a log into Zoom, go out, have a cup of tea, and then come back and log out, thinking that attendance is mandatory, right? So I'm mentioning this right away, right? So you can stay. I'm not pushing you out of the session. That is not my intention. But if you think you have to be here for the sake of attendance and certificate, no, that is not the case. You can drop off if you want to watch this later, right? So if you want to interact, if you want to be here and see what happens, you're free to do so. I'm not going to stop you from doing that. But if you have other intentions, then you can feel free to drop off right away and watch it offline, right? So we won't count that against you. So that is something that I wanted to mention. And the OPP will be conducted in Feb, sometime in the second week of Feb. And the fee payment link, we will send it out after these 4 days, right? So sometime next week, we will send you the link to pay the OPP fees. Right? There's some 500 rupees or something that you need to pay to register for the OPP. Okay, so is this part clear to everyone? Whatever I've just mentioned?
Excuse me, sir.
Yes, sir.
Yeah.
Sir, we have our balance in our wallet. So can we use that?
So that part I'm not sure. So whenever that comes up, there'll be a detailed mail that will be sent out to you, right? So I'm right now not sure about the fee payment part, but yeah. Okay. Yeah. So then let's get started. So I hope my voice is clear and there's no noise from my end.
No, it's crystal clear. Yeah.
Okay. All right. So we have 4 days, right? So today we'll discuss a bunch of libraries, right? So NumPy, Matplotlib, SciPy. We won't do SciPy a lot, but we will discuss some aspects of NumPy, Matplotlib for plotting. NumPy is for numerical Python. It's called numerical Python, and it is for mostly the linear algebra part of machine learning, right? So that is what we use NumPy for. SciPy you use for several things, but from the point of view of MLT, we use it for optimization. Okay, so there is some optimization that happens in almost every week, right? So mainly we'll be using it for SVMs. That will come on the last week. Okay, so today we look at NumPy now and Matplotlib, right? So these two libraries will be the main focus. As you can see, NumPy is in larger font compared to Matplotlib, and that is intentional, right? So there'll be more of NumPy in slightly less of plotting, but we'll do both of them. So moving on, few more things. So as mentioned before, all these collabs, you can find them here, right? So tiny.cc/mlt_workshop. So please make a note of this. And yeah, right. So we'll go from, so each collab will be about a particular topic. Okay, and you'll see that as we go along. So what you can do is you can either code along with me, or since all these sessions are going to be streamed, you can just watch what happens and then code later on. So all the solutions have also been provided for these collabs. So each day there are some 5 or 6 collabs. So today there are 6 collabs, but next few days there'll be, I think, 1 or 2 collabs. So you'll have solutions for all of them already provided in that particular folder, right? So you don't need to necessarily take down anything in the form of notes or anything, right? So
Sorry, sir, I joined late. Where is that folder? So can you please?
where is what?
Where is the folder for all these files?
Here. Okay, so
Can you paste the link, sir?
no, it's too simple to paste. So I just
Okay.
hope one of you will do that for me, right? So,
Okay.
right. So this is tiny.cc/mlt_workshop, right? So you can just write it down. Okay, so I just request, if in case someone asks in the next 5-10 minutes, please help me out with this part. You can paste this link on chat. All right, so that's the plan. Now let's get started. So one thing that you'll have to do is, these collabs will be in read-only mode, right? So you'll have to copy them to your drive if you want to edit them. So if you open any one of these collabs, you will see a copy to drive option. You have to click on that and that'll enable editing. You create a copy of this collab, your own copy, and you can start working with it. Okay, so very briefly, we look at these 3 libraries, what has happened in the last 20 years. So these were created about 20 years back. So matplotlib, for example, is 20 years old now, right? So 21 years old. And they have been some of the most important libraries for scientific computing, right, in Python. So NumPy is still relevant. I am not going into this survey, but you can go check it out. This is the screenshot that I've attached here is 2022, but there is a 2023 survey also which has come out last year. Okay, and Python is one of the most popular languages according to the survey, and NumPy is one of the most important libraries or frameworks that people are learning, right? So especially if you look at professional developers, around 24% of them use NumPy in their professional lives, and that's like the second in the list, right? So NumPy is still very much relevant, and of course, those who are learning to code, if you notice this part, nearly 42% start learning to code using NumPy, right, as a library. So it is still relevant. Now, if you compare it to other frameworks, it's still somewhere, right, in the picture. It's not like totally out of the picture. So it's still there somewhere. Right? So NumPy is something important that we all have to know about. Okay, so what can we do with NumPy? We can do quite a lot of things. The first part, right, for the first 20 or so minutes, we'll be looking at how to represent vectors, right? So vectors have been one of the most important objects in machine learning techniques, right? If you think about it, every sample that you can think of, right, has been represented in the form of a vector, right? So this could be, you could call it a feature, right? So this is feature 1, this is feature 2. Say maybe feature 1 is height, feature 2 is weight in whatever units. So you can think of this vector as some kind of a sample coming from a real world practical setting, right? And then of course you could go on to the abstract version of a vector, which is something which has a direction, magnitude. You could think of it that way. We're also used to thinking of vectors geometrically, right? So this 3, 4 is actually a point in 2-dimensional space. So we often call it a data point. So in MLT lectures, you would have, if you have watch them. Notice that professor mentions that this is a data point several times, right? So we think of it geometrically, we think of it algebraically, we can add two vectors, we can multiply them by scalars, right? All these things we know about. But what we are concerned with is the computational side of a vector, right? How do we make a computer understand a vector? And of course, a collection of vectors which turns into a matrix, right? So how do we make a computer understand these things so that we can convert our machine learning algorithms, which are essentially mathematical steps of mathematical statements, right? How can we convert them into computer code, right? Which a system will be able to process. So that's the whole point. So how do we represent vectors in using Python as a language, right? So this is where NumPy comes into play. So NumPy has this idea of a array. So it's array. I've done PDSA. You will know this. You've seen NumPy array. So Professor Madhavan introduced this in PDSA also, right? So NumPy array is very similar to a Python list, but at the same time very different from a Python list also. So it's a much more powerful object than a Python list. Okay, so let's now get started with our first collab, right? So this is going to be our first collab. So first thing is you just import NumPy. So this is the way you import it, right? So you import NumPy, the package called NumPy, and the way you call it, right? What you refer to it is NP. You could just import NumPy alone, right? So you could just import it as NumPy, but it's more convenient to give it in what is this called an alias, right? So it's a different name for the same package. So instead of calling it NumPy everywhere, we are going to call it NP. So we are importing it as NP. Okay, and once you import it, NP is what you will be using. So so far, I hope everyone is following, right? If you have any questions after a point of time, you can stop me. Otherwise, I'll just move on.
I just have one basic query. So is it recommended to use this Jupyter notebook only, or we can use some other editor as well?
You can use anything. It's not necessary that you should use this Colab or some Jupyter notebook kind of editor, but Collabs are convenient because they reside in the cloud and they get auto saved, and it's very easy to share it with others. It's easy for others to comment. So yeah, for various reasons, we prefer Collabs.
Yeah. So like one challenge that I have always seen is the help text in Colab. So that would be there. However, in other editors, that help text is very helpful.
Sorry, what is that?
Help text, right? Like if we can just press dot and go for the search for the desired method.
That is there here also, right? Here also it is there.
It's there, okay.
Yeah. In fact, it's much more convenient here. If you get a lot of, you can do it much more. Okay, so that is Collabs, right? So now we get started with Python lists. So Python lists are, you already know this, right? Now, I'm not going to tell you why NumPy arrays are better than Python lists right now. We'll figure it out. So I'll jump into arrays directly. Right? So how do we create this vector? So this is a vector. What you see here is a mathematical vector. So the way you create it is, okay, let me just, so this is just a Python list, right? 1, 2, 3 is just a Python list. Now, to turn it into a NumPy array, this is what you do. Right? So np.array of the list 1, 2, 3. So that turns into what is called a NumPy array. So you can print X. You can also see what the type of X is. Right? So if you the type of X, you'll see that it's called a NumPy ND array. So why is it called ND array? That we will discover as we move along. Okay, so this is what an array is. So one feature in Colab that's very useful is, instead of printing stuff every time, what you can do is whatever you want to see as output, you can just mention that as the last line in your cell. Okay, so this whole thing is called a cell. So This is called a cell, and if you want to find out what is there in a particular variable, in this case I have only one variable, x is that variable. I want to see what is stored in that. So I can just type that, make that the last line of my cell. And if I run this cell, right, so I can either press this or I can do control enter. So both of them are valid. That will run this cell, and the output, or rather the contents of the variable x, will be displayed here. So this is a shortcut that might be useful. So for those who join late, since there are like 200 odd, I just once again mention this in case you are here for the attendance. You don't need to worry. So attendance is not mandatory. The session is being streamed. Okay, so every now and then I want to keep saying this, so you are not here by compulsion. Okay, so yeah. Okay. So that is,
Sir, can you show once again the type?
yeah, type of x. So you can just, I'll just do the type. Okay, so that is an NumPy array. Now let's move on, right? So this is, so we have seen, yeah, so this will give us more space. So what we have seen so far is how to create a simple vector. Okay, so vector and NumPy array, currently we'll be using it interchangeably. So we have created one array. Now we can add these two vectors, right? So we can, this we can do in mathematics, x plus y. So let's see how that translates to in NumPy, right? So let's first create first vector x and then vector y, right? So now x plus y, right? So this is how you add two vectors. Notice how seamless the transition is from the math part of it to the code part of it, right? So this is NumPy. This is what you have to really understand, that NumPy is written so beautifully that you can seamlessly move across mathematical statements and computer code, right, or Python code. So there is, if someone is looking at this, if you just plug the statement out, it's very hard to tell whether it's a Python statement or it's a math statement, right? So that is the power of NumPy. So once you create these vectors, these operations look very similar to the mathematical counterparts. Okay, so this is how you add two vectors. Now,
So NumPy array is same as vector, right?
at this stage, yes, you can assume that, but it's NumPy array is a much more powerful object, right? So we'll come to that. For now, what you can think of this as NumPy array is helping us define vectors in Python. Okay, it'll help us define matrices also in Python. So we'll come to that. For now, it's helping us define, manipulate vectors. Okay. So there is, so we'll be looking at a bunch of operations. So one is addition. So the next operation is multiplying two vectors element wise. Okay, so this is often called the Hadamard product. So this will come up in several places in machine learning, right? So this is, I'm again defining these vectors. So I create the list and then enclose that in the NumPy array. That's the way to do it. So z equal to x star y. So if you want to multiply something element wise, this is the way you do, right? So you just use x star y, and what that will do is that will just multiply the two vectors element wise. Okay, so that's what's going to happen. Now you have to be careful here. So if you define two vectors of unequal length and you try to multiply them, naturally it will throw an error, right? It will say that operands could not be broadcast together with different shapes. Okay, so you have to be careful about the shapes when you are defining them. So I'll come to what shape means, but I hope that was clear. Okay, so next comes, yeah.
Excuse me, sir. If the NumPy array is, whether it is taken as row vector or column vector.
Okay, that's a good point. So for now, assume that it's taken as some kind of a row vector, but it will become that part will become very clear soon.
Okay.
Okay, so the next part is scalar multiplication, right? Recall that's the second important operation as far as vectors are concerned. So this is again very simple. So first define your vector and then just do 3 into x. I'll keep repeating this part. Notice how similar the math expression is and the Python expression. Okay, so this multiplies each component of the vector by 3. That is what scaling means. So scaling is just increasing the length of the vector in some sense. Okay, so that is scaling. And now there's a lot of text here, so I'll just come down and show the example. So what we are doing is here we are applying a function element, right? So if the vector is 1, 2, 3, 4, we want to square each component. So how do we do that in NumPy? So we have the vector 1, 2, 3, 4, and we want to square each component. So the way to do it is whatever function you need to do, just think of x as a very simple scalar value. If x is a scalar value, what would you do? You'll just say x squared. Okay, the same thing works with NumPy. So if you do x squared, notice that you get the individual components of the vector have been squared. Okay, so that is one very simple example. Now you can also do it for other kinds of functions. So this is slightly more involved. Algorithm, you want to compute the log for all these components, right? You want to do this for all these components. So let's first create the initial array. So 10, 100,000. This is 10,000 and this is 100,000, right? So this underscore is just for ease of reading things out, right? So it's just a separator between the thousands place and the remaining place. Okay, that's just a Python code, right? So once you have x, what we need to do is we need to apply this log function on each of these components, right? So the simple way to do it in NumPy is the NumPy has a log function. Okay, so if you don't know what this does, so any function in NumPy, if you don't know what it does, there is a way to know its signature, right? So, and this is how you do it. You write down the function and then you add a question mark after it and you run that cell. Okay, so that will give you the signature of the function and the doc string basically, and also other parts. So for example, here it's telling you, sorry, just give me a second. Yeah, so this is the help part, right? So what it's telling you is, this is the signature np.log and come down to this part, right? So this computes the natural logarithm, right? Log to the base e, and it does it element wise. Okay, so what are the parameters it takes? It takes some array, input array, right? So here the array is 1, 10, 100,000, so on. And there are several other things which we don't need. Let's just go to what it returns. It's going to return the natural logarithm of x element wise. Okay, so the other nice part is it will also give you related functions. For example, log is there, but then log 10 gives you log to the base 10, log 2 gives log to the base 2, right? So all these things it gives you. So what we need is log to the base 10, right? So the function we are looking for is this. So let's go back. So log 10 of x. Yeah, as expected, log 1 is 0, log 10 is 1, right? So this is what you will get. Okay, so these are not random exercises, right? So what we are doing now is very relevant from a machine learning context. So if you look at, so yeah, so can someone tell me where log comes up in ML? Those of you have just completed MLT.
Sir, likelihood.
Okay, log
For
log
maximum
likelihood.
likelihood. Yeah,
That's a good
maximum
place.
likelihood.
Anywhere else where we saw log in MLT?
Or we need to move the equation of the regression to the standard equation.
Log loss error, sir.
Loss function.
Okay, loss function. So there was
Logistic regression.
Logistic, sir. Logistic.
Okay. Did it come anywhere in decision trees?
Yes, sir. Information gain.
Yes, sir. Information.
Capacity, entropy.
Entropy.
Right.
Entropy, Gini, information gain.
Okay, so whenever, yeah, thanks. Yeah, those are all valid, correct answers. So I just want you to always relate to the MLT course, right? So we are not doing things randomly. So why are we suddenly looking at logarithm? Because it does make an appearance in ML, and often we take log on vectors like this, right? So for example, all your data sets are matrices. So you have to take log for a particular column, maybe. So you need to do this kind of an operation. So that is where you'll be using something like np.log 10.
So in the array why you have given that underscore, can you please comment again?
Yeah, so that's just a Python. It's a way of writing long numbers in Python, right? So for example, I want to say write down 1,234,576,678, something like this. This underscore gives me a nice way of writing it. So it's the same as, if you look at it, it's the same as this number 1,234,576,678, but then underscore makes it more readable. So just like what we'll do, right?
Okay.
We'll do 1,234,576,678. So it's the same thing, but in Python, it's not the comma. Okay, so yeah, that is np.log10. Now, you could also
Actually, when you had run that function, not the underscore one, the one before that, when you ran it, it returned an np.array, and there was, after each of the numbers, there is a dot or a full stop or however you call it. So why is that coming?
Okay, that's because it returns a float value, right? So this is, if you look at the signature of log 10 and look at the return type, right? So the return type, where is the return type? Okay, it's not mentioning it here, but it returns a float value. So if you look at, let's call this z equal to or y equal to np.log10. And if you look at y dot, I think there is a attribute for, so y is an object, right? There is an attribute for it called d type. It will tell you what is the type of the components inside this array.
Oh, okay, got it, sir, got it. Thank you.
Yeah, right. So that is okay. So this is, maybe I just noted, right? Why are there dots after the numbers? So this is the answer, right? So that is that part. Now we can likewise do this for in some other array. So in this case, so there are two constants we keep looking at, right? So one is, let me first mention this. So np.pi will give you the value of pi, right? I'll just, so these are useful constants that come up in machine learning math, right? So the other one is e, right? np.e. So these are built in to NumPy, right? So you can directly access them. Okay, so what we are going to do now is we are going to define this array. So this array is nothing but an array of powers of e. Okay, so this is one np.e, np.e square, np.e cube.
8:30.
Now you need to take the log of this. So just log means natural logarithm. So that will give you 0, 1, 2, 3, right? Log to the base e.
Sir, actually, in 26, np.pi, it didn't print it. It printed only np.e, right?
Okay, no, I didn't run it.
Okay, right.
Yeah. Okay, so that was those two examples were logarithm based. Now, so just like scaling vectors, you can do slightly more complex things. You can Now add some number to every component of a vector, right? So if you have a vector like say 1, 2, 3, and you have to add 5, this number 5 to each component of that vector, it's done very simply like this. Okay, so this operation is sometimes called broadcasting. What will happen is, I should have talked about broadcasting before. So if you recall, there is this part that we did, right? Scaling a vector. So 1, 2, 3 is a null vector, and we wanted to multiply this by 2, right? That is what we did before. So we did this here. So 3 times x, right? So we did this scaling by 3. Now assume that we are scaling this by 2. So internally what happens is this operation is called broadcast, right? So you are multiplying a scalar with a vector. So you can think of this conceptually as so 3 copies of 2 being created, and then element-wise multiplication happening between these 2 vectors. Okay, so this is again conceptual. This is not how it happens. So what happens in NumPy is different. But if you want to understand how this scalar multiplication, or this, instead of star, it can also be plus constant, right? So how these operations happen, you can think of conceptually this happening, right? So the scalar turns into a vector which has the same number of elements as the vector it needs to multiply with, right? So, and then you do it element wise. Okay, so this is one way of understanding how these operations happen, and this is called broadcasting. Okay, so in fact, I leave this. It's not very important now, but you can read more about broadcasting online in the NumPy docs. For us, it's right now not very relevant. Okay, so even though it's very important. Okay, so is this okay? How to add a constant to every component?
Yes, sir.
Okay, so this is okay. Once you are able to do that, next we start coming to functions, linear functions, right? So it's a linear function of a vector. So these, where do you think this kind of a function will come up in machine learning?
Regression.
Okay, in some cases like regression, right? Yeah, so that is that. So let's quickly do this. -1, 0, 1, 2. Now you have already seen this. It's a combination of 2 operations. You are scaling a vector and then adding some constant to it element wise. Okay, so if you actually compute, you will get this. So again, I want to draw your attention to this fact. NumPy expressions are similar to the mathematical expression. So that is important to note. Okay, so that brings us to perhaps the most important operation in all of machine learning, which is the dot product, right? So every week you would have seen the dot product come up somewhere, right? So W transpose X, some classifier for regression also it's W transpose X. Neural networks also it's some W transpose X, right? So everywhere you will see the dot product. So no machine learning without the dot product. Therefore, we have to discuss this right away. So you have 2 vectors. Let's call them A, X, and Y. So -4, -5, -6, -7. So NumPy provides a function to do this. It's called np dot of x comma y. Whatever you want to compute the dot product of, just give those 2 vectors as arguments, and it will give you this. And you expect this to be the same as y comma x, right? It's symmetric. So the operation is symmetric. So you can just give x comma y or y comma x. However, there is also another way to do this, and that's a much easier way. So this is called X. This is the ACT operator that was introduced in Python 3.5 to work alongside NumPy, right? So this will do matrix multiplication for us. Okay, but it's, if you use the right operands, right? In this case, we have used vectors on either side. It will end up doing the dot product for you. Okay, so this is we'll come back to this. For now, just you can think of this as dot product, right? At is giving you dot product if you use vectors on either side. Somehow magically x becomes a row vector and y becomes a column vector. So that's the image that you have to keep in mind. Okay, but we'll come back to this in like 2 more collabs. We'll be discussing this. Okay, so you could use np dot dot. I would suggest that you stick with x at y.
What if both of them are like linear?
Sorry,
not
both of them
vector.
are?
But like both of them are not vectors, then what will happen with that grid?
We'll come to that, right? So there are like four different cases. What happens when one is a matrix? What happens when both are matrices? So we'll discuss that. Okay, we'll discuss that very soon. Okay, so sometimes you might want to have a vector of zeros. So where in MLT have you seen a vector of zeros? In which algorithm was this used? A zero vector?
Subtron. Initial bits.
So yeah, that's so first subtron started off with the vector of zeros, right? So W equal to np dot zeros is the way you do it. So if you want 5 zeros, then you just say W equal to np dot zeros of 5. Sometimes you want just a bunch of ones, right? So then you say np dot ones of 5. 5 is the number of ones you want, right? How long the vector should be. Okay, so this is one question. So if you wanted a vector where all the elements are equal to 5, how will you do it? 5's.
Multiply by 5.
np dot
You
1
will just multiply the 1
multiplied
into
by
5.
5.
Okay, right. You just multiply the ones with 5's, with 5, right? So that will do it element wise. Therefore, we'll end up with this. Okay, so that is those are 2 useful functions. Next, you have.
Excuse me, sir.
Yeah.
Sir, can we use something like list comprehension as we use in the Python lists normal?
Yes. For you could do that, yeah. But when you have custom functions like this, it may not be. It's not wrong using list comprehension, but since NumPy already gives you utility to create a list of ones, you can just go ahead and use them. Okay, so yeah, sometimes we might want to have a sequence like this. Okay, first n natural number. So in Python, you do this as follows, right? List of range of 1,6. So that will create a list from 1 to 5 for you. NumPy provides what is called a range, right? So a range. So start index, same like Python, right? Only difference is that it will give you a NumPy array instead of a Python list. Okay, so this is what happens. So this is, again, you will see that this is a useful function to have. All right, so now,
could we go to the previous one? Yeah, this list range of 1,6 required to be given in np.array before. First line is useful, sir.
No, right. So first line is Pythonic way of doing it, but for NumPy, this is enough. Yeah.
Okay.
Okay, so that is the range. Now we come to some other useful operations like norms, right? Norms you have seen, you have done this so often, right? So there are several places where norms come up. So NumPy has some modules which are pretty useful. One such module is a linear algebra module, right? So it's called linalg, right? So if you just try to press tab and see, you will see there are so many things that it does, right? It can find the determinant. It can give you the eigenvalues and eigenvectors. It can only give you the eigenvalues, or it can give you both eigenvalues, eigenvectors. It can compute the inverse. It can give you the rank of the matrix. It can give you the norm of the matrix. It can give you the pseudo inverse, right? It can solve a system of equations. can give you singular value decomposition of a matrix, right? So many things. So it's a incredibly powerful library, submodule or module in linear algebra, this NumPy library. What we currently need is this norm, right? So what we need is norm. If you just type in np.linearalgebra.norm, it will give you the Euclidean norm. Okay. If you want a different kind of norm, right? So let's say you want the L1 norm, the Manhattan distance, as they call it, from the origin. So you have to give in this argument called order, right? What is the order of the norm? So if the order of the norm is 1, that will be this L1 norm. So if it is 2, that is the default value, you will get the Euclidean norm. So if you don't type
Can you explain again, sir?
Yeah, sorry.
Can you explain again, like this lineal.norm part? Whatever the parameters it take.
Only two that we are interested in, right? The vector and the order. What kind of norm you want? You want an L1 norm, L2 norm. If you want L2 norm, you can just, if the usual Euclidean norm, right? That is just np.linearalgebra.norm. So if you want something more specific, like the L1 norm, you specify that as the order. Okay.
Sir, and what if the order is 0?
Then you will get what is called, I think, max norm. So that will give you the maximum of 1, 2, 3, which is 3. So that's L0 norm, right? L0 norm is the maximum of the components. So it will give you that particular norm. Right? So this is the usual Euclidean norm. And this is the L1 norm. Usually we just use these two, right? We have used only these two in our course. So L1, L2, where did we use L1 norm?
Lasso regression.
Correct, right? So lasso, and L2 was used in ridge. So these are again used in the course, right? So hence we are doing it here. Maybe I'll just mention this so that we don't forget.
Sir, order 2 is Euclidean and order 1 is?
The L1 norm, the Manhattan distance from the origin, right? So that is the L1 norm, sum of modulus of components. Okay, so now we come to a very critical concept in NumPy, which is called the shape and the dimension, right? So we have to be careful here. So we have been used to looking at the dimension of a matrix or a vector as the number of components that are therein, right? So we say that this vector is 3-dimensional, meaning it lives in R3, or this matrix has dimension pi cross 4. Okay, so we are used to saying these things, but NumPy has a slightly different connotation to these things. So there is the idea of shape, right? So shape is actually the number of elements in your vector. Okay, so this is a tuple. That's why you're seeing this as 4 comma. So it's a tuple. So it's a tuple of size 1. So when you see a tuple of size 1, that means you're dealing with a vector. Okay, so this is the shape. Shape means number of elements. Number of components. There is also what is called the NumPy dimension. Okay, so the NumPy dimension here is 1. Okay, this should not confuse the NumPy dimension with the vectors dimension in the mathematics, right? So the vectors dimension is what? The dimension of the space in which this vector lies is 4. Lives in R4. Okay, so that is 4. That is plane dimension of the space in which the vector lives. But ndim is what is called the NumPy dimension. So for certain reasons, this is single dimensional object. Okay, you can, why is that? It's because you can just write it in one line. Okay, if you want to write down a vector, you just need to go from left to right or top to bottom. So you just go in one dimension. You don't need a table to write down a vector. You need a table to express a matrix, right? A matrix is nothing but a table of numbers. So therefore, a matrix is 2-dimensional, as we will see in the next set of collapse. But a vector is linear, so it's just 1 dimension. And that is what ndim means, right? NumPy dimension. Okay, is this fine with all of you? Okay. So that is the end of the first collab. Now, move to plotting simple curve. Let's just break for 2 minutes and then we'll begin again. Okay, so let's resume. So this collab is about plotting, right? So plotting some very simple curves. So I didn't mention few things, right? So yeah, before we move to curves in matplotlib, I just want to mention this part. Okay, so this is again the part that I've been mentioning all along, which is how easy the transition is from mathematical expression to number. So it's just a quick summary of what we've seen so far, right? So x plus y is x plus y, x adamant y is x star y, x transpose y is just x at y, right? Ax plus b is ax plus b here. So please keep this in mind. The transition is smooth. So that is one part. And now we can move on to plotting, right? So just NumPy is an important library for numerical computation. Matplotlib is the library that we will be using for plotting functions. Okay, so this is what we need to plot any function, right? So you have, let's say, f of x, right? You need to plot f of x against x or some y values against x values. The first thing that we need is a collection of x values that are maybe distributed uniformly along a line.
Are you writing something?
No.
Okay.
Yeah. So we need a set of x values that are distributed along a line, and the function that helps us here is called the linspace, right? So what linspace does is it partitions this line into equally spaced intervals. Okay, what do I mean by that? So let's look at what linspace does, and then we'll get an idea. So you have 0 to 1, and you want to divide it into two equal parts. right? But then there should be 3 points on them, right? So if you want to divide a line into two parts, you need to specify 3 points, right? So 0, 0.51, 3 points. So if you want to divide it into three parts, you need four points, right? So 0, 0.33, roughly 0.661. So this is what linspace will do for you. You don't have to manually calculate 0.33, 0.66. That will calculate it and give you the array, right? So likewise, if you want to divide it into 4 parts, or if you want to divide it into equally spaced points that are with 5 of them, this is how you do it, right? 0 to 1, give me 5 points which are equally spaced. So this includes the endpoint, right? Endpoints. Likewise, you can go to 6, 7, so on, right? So this will divide it into 6 parts. So it will become clear why we are doing this. So let's first write this down in np.linspace between 0 and 1. If I try to divide it into equally spaced intervals with 10 points, this is how I do it. Okay, so if you now look at the shape of x, recall that the shape of x is number of components in x. It has 10 components, right, or 10 elements. Okay, so this is how it looks like. The interval size is constant. It is 0.11 here. Okay, so first, let's go and do the first plot. So we have to plot y equal to x. That's what we have to plot. So what we'll do is, we'll first create x coordinates and then look at the y coordinates, right? So we want to divide the x. So we are plotting only from 0 to 1, right? So I'm dividing 0 to 1 into 10 equally spaced points. And then I have been asked to plot y equal to x. So y is just equal to x. And I'm going to use PLT. If you notice, I have imported matplotlib.pyplot, right? This module pyplot lives inside the library called matplotlib. And I'm importing it using this alias or different name called PLT. So I don't want to keep using pyplot everywhere. So I'm calling it PLT. So what do we do here? PLT.plot. PLT, inside PLT, there is a function called plot. So that will help you plot y versus x. But the way you have to enter the arguments is x comma y. Okay, so if you notice, you get the x equal to y plot. So this is a simple curve.
What if we just pass x?
And nothing will happen, right? It won't plot. You need to throw an error. Or doesn't throw an error?
Nope.
Okay, that's surprising. I have never tried this out, but I'm hoping you will want to plot something against something, right?
Yeah, that part I understand, but I just wanted to see what happens.
Okay, yeah, I am surprised by this behavior. I have never seen this before. Perhaps there is something to do with the signature. Maybe we can explore that, right? Please explore this part. But in general, you will want to plot something against something. Okay, so please include an x and also an y.
So what is this linspace to? The first statement?
So the linspace, as I mentioned before, right? So it partitions the x-axis into equally spaced points, right? So it's going to plot, for example, here what it's going to do is, at the point 0, it's going to plot y equal to 0. At the point 0.11, it will plot y equal to 0.11. So you think of, yeah, this slide is there, right? So think of how you used to plot functions in your school days, right? So this is what you used to do. You used to select a bunch of points on the x-axis, and then you used to plot the corresponding values on the y-axis, and then you are used to join them by a freehand curve, right? So what np.linspace does for you is, it gives you these points on the x-axis against which you have to plot your y values. So linspace will give you x1 to x4, for example. Okay, so that is what linspace does for you. So this is not quite clear, you can do what is called a scatter plot. We'll come to this later, but the scatter plot will give you a very clear idea of what's happening, right? So there are actually 10 points here. Between 0 and 1, linspace has given you 10 equally spaced points. Corresponding to each of them, you have plotted the y value. So that is this blue dot that you see here. And what matplotlib does is, when you ask it to plot x comma y, it will connect all these points by a straight line. Okay, it will connect consecutive points by a straight line. This is exactly what we do when we are asked to plot, right? So in our maybe 10th and 12th classes, this is what we do.
Sir, if we use y is equal to x square over here in line number 2, so will this plot function plot something for us? Like
yeah, so that's the next one. Yeah, we'll come to that.
okay.
Right, so we'll come to that after we do a few more examples. So now it's not a simple y equal to x, it's something different. So what we have been asked to do is sample 20 points in this interval between minus 5 comma 5. So this is 20, right? So 20 points between minus 5 to 5, that will be your x. Okay, and if you look at x, it will look something like this. Okay, minus 5, minus 4.47, whatever. So if you look at the shape of x, that is 20. There are 20 elements there. Okay, now you have to plot y equal to 5 minus 3 times x. So as before, you just give x comma y. That will plot y equal to 5 minus 3x for you. But we have also been asked to add a title to the plot. Okay, and the title should have the equation of the plot. So this is just, there is a command, there's a function called title. So you just call this and you end up with the title on the top. Okay, so sometimes what will happen is, not sometimes, always what happens is, if you recall what I mentioned earlier, whatever you type on the last line, the value of that expression will get printed. Okay, so the value of the last line in this case is some output like this. Okay, this is something written by matplotlib. So you don't want this. So I don't want to see this output. In that case, what you have to do is you have to add a semicolon here. Okay, so if you add a semicolon, that particular output will be suppressed. That won't be shown by the Colab. Okay, so that's just a minor tip if you are interested in getting away with this extra output.
So this feature is just for Colab, is it?
This is only for Colab, yeah. At least that's the one I know. I don't know
Not
if
only
that
for Colab, actually it works
It's
in
for the
all IPY
all the
and
IDE, yes.
Oh, is it?
It
Okay.
works on all the IDEs.
I've never used Jupyter notebooks or other IPy notebooks that much, so I know only about Colab.
Currently, I'm using it in VS Code and it's working.
Okay, yeah.
And I'm doing in Jupyter Notebook and it's working.
Okay.
Because it's not showing in Jupyter, so that's why I was curious.
Oh, is it? Okay, I'm not sure, but in Colab, if you want to suppress it, I am sure this works. But others, I can try.
Yeah, maybe some setting it should as well. Yeah. Thanks.
Excuse me, sir.
Yeah.
Sir, if we use scatter in place of plot, what will happen in line number 3?
Okay, if you comment out plot,
it will just show dots also.
Yeah, it will only show the dots because scatter is just
okay.
plot x against y. If you want to see both, then you
right. Okay, sir.
Okay, so this is 5 minus 3x. Now,
thank you, sir.
Yeah, so now we'll come to parabola, right? So we have to plot y equal to x square. There are 4 plots that we'll do, right? So first we have been asked to do it with 5 equally spaced points, right? So this is
9 o'clock.
np.linspace of minus 1 comma 1 with 5 points, where we are asked to plot y equal to x square. And let's plot it, right? Let's first plot it and see what happens. Okay, so this is what you get. Now, do you see why this is happening?
Because it's linspace. Yeah.
Right. So just it's because of the point that I mentioned.
A plot connects everything by a straight line, right?
Exactly, right? The straight line point that we were discussing earlier, right? So what matplotlib does internally is it's going to connect all these dots by a straight line. Okay, so if you choose a linspace, a spacing that is too coarse, a coarse spacing will be something like this, where the interval between points is like quite large, then you have with a visually incorrect graph, right? So whatever, even if you make this really high, at the back end, what's happening is it's doing line plots only, but at least visually it will be much better, right? So let's change this to 10 and see what happens. You are using more points to plot, so it's looking slightly better, but I can still make out line segments connecting consecutive points. So if you make this 20, it's quite smooth. So I'll get rid of the scatter. We don't need the scatter now. Okay, so even now you can, if you actually watch closely, you will notice that you can still see the line segments, right? So small line segments here. So when you go to something like 50, as far as our eyes are concerned, it will be indistinguishable from a parabola, which is a smooth parabola, right? So make sure that you choose the number of intervals or number of points on the interval carefully. By default, linspace makes it a point to include 50 points. Okay, so you don't need to specify if your interval size is in a particular range, and if you're at the right zoom level, you don't actually need to mention how many points to take, right? So I'll just show you using a question mark. You'll see that the number, right? The num here is, so the parameter num is there. Num is the number of samples to generate, right? And by default, num equal to 50. Okay, so you don't actually need to mention the num parameter here, but if you mention a small parameter, then you're in trouble. Okay. So that is a parabola.
One question, sir.
Yeah.
What if we want to take exclusive?
Exclusive?
Like not -1 and 1, just the points in between.
In between what?
Like we do in maths now, like when we take the round brackets, we ignore the outer points.
You ignore you mean on open interval, closed interval business, or?
No,
Yeah,
here
like
this linspace is a function, so it always take an inside round bracket. So he's asking if we are using this round bracket, if -1 is excluded or included.
Yeah, so I think there is a way to fix the endpoint.
So just by incorporating plt.scatter, his question will be answered.
Okay, so if you set endpoints equal to false, that will. So if you look at endpoints, I'm hoping you're asking about open and closed intervals. If I'm not mistaken.
Yes.
Yeah. So if you want an open interval, currently it's using a closed interval, meaning endpoints are included. So if you want endpoints to be excluded, I think you have to set endpoints equal to false. Endpoints equal to. So if you use endpoints equal to false, does it? Let's try it out. I don't know. I need to check this. So let's try endpoints equal to false and see what happens. So np dot, let's say, so it's not closing. Give me a second. Yeah. So np dot in space of, let's say 0, 1, 3, right? So this was giving us 0.5. If you say endpoints are false, will it give 0.5 alone, or endpoints or endpoint? Okay, it only excludes the right endpoint. I'm not sure how you'll have to, if you really want to exclude this, then maybe you can go for something like start with a very small number after 0, or maybe 0.001, so that you don't hit upon 0 and exclude the right endpoint. But this doesn't seem to exclude the left endpoint. Okay.
Isn't there any parameter called start path? Can we check?
I didn't get you.
Sir, I'm asking, isn't there any parameter called start path? Can you check?
Is there a parameter called
Start point is saying.
start point? Start point is this, right? -1 is a start point,
Yeah,
right?
like we have a function, na, endpoint. So maybe there is an option called start point also. Like maybe.
Then, so sorry, so there is a start point, there is an end point, right? In the interval.
No, actually, like we have
he's
a
saying
parameter
we have,
called endpoint, na?
Okay, I'm not sure. You can check
sir,
that.
he's saying we have a parameter named endpoint, so there might be a parameter called start point. He's asking just can you check please?
Okay, that you can check, right? So right now that is not too important, but please check that yourself, right? So I think you can figure that out, right? So this is not too relevant from the context of plotting, right? So you usually have a start point, end point. So you can see this start point being excluded, included is not too much of an issue in your plotting curves like this, right? So visually, how it's not going to matter too much, right? If you're only interested in the visual aspect of it. Okay, so what did we miss here? We are also asked to add the x-axis and y-axis, right? So we have plotted. Okay, so we know are going to add the x-axis. So this is one way to do it. There are each website will give you some other way to do it. So this is going to add a horizontal line, ax h line. This will add a vertical line. Okay, so this is the axis. But then they're all in the same color. So what you can do is to distinguish the axis from the actual plot, you can add a specific color to your axis. Okay, so that will make it black. Okay, there are other things you can do. So you can make this marker a dotted line. I don't know how to do that here. You can search for it. So the nice part is all these things are available online. So you can go to the matplotlib website and search for it, or you can ask ChatGPT, right? So that will give you the answer. Okay, I'm only giving you the essentials here, just enough to get you started. There is a lot of room for exploration changes here.
And it will draw horizontal and vertical line with 0, 0, sir.
Yes, yeah.
Okay.
Okay, so now we have to plot this slightly few more tricky things, right? So how do you plot parallel lines? The lines parallel to the x and y axis. So you have to plot y equal to 3 and you have to plot x equal to 5. Okay, let's quickly do this. So let's first do the easier one. Easier one is y equal to 3, right? So that's the easier part. And we have to limit our region to x being 0 to 6. So what will the linspace be? It will be 0, 6, right? So you have to plot between 0 and 6. So you have to plot y equal to 3. So I want someone to think of how you do this. So plt dot plot x comma y. I need to plot y equal to 3. So what should I plug in here?
Ones of 1 into 6 into 3.
Okay, np dot ones. Okay, of certain number of ones into 3. That's correct. So what should go into this?
6.
50.
Yeah, 50 should go, right? Because you are using this for every point on x, on the x-axis, you have to have a corresponding point on the y-axis. So here we were having 50, right? So by default it is 50. Maybe we'll just say explicit. Let's make it explicit. So you have 50 points. The x-axis is partitioned into 50 points. So your y-axis will also need to have 50 values. Okay, so if you plot this now, between 0 and 6, you have y equal to 3. Okay, now let's plot.
How you come to this 50 path, sir? I didn't understand.
Because this 50 is there here, right? So we have chosen 50 points into which we are dividing the line 0 to 6, line segment 0 to 6.
Okay.
Okay, so if you don't do this, what will happen is you give this something like 51. If you make this 51, so matplotlib will throw the error that x and y should have the same shape, but then they have shapes 50 and 51, which is incorrect, right? So you have to have the same shape. Okay, so once you plot x, y equal to 3, how do you plot x equal to 5?
NP dot once into 5.
Okay, so what we have to use here is the y value is going to be going between 0 to 6, okay? And the x value is going to be set at 5. Okay, so if you plot this, you get x equal to 5. Right, so this is how you plot x equal to 5, y equal to 3. Now you can, of course, start giving. So I'm going to color this, make this explicit. I'm going to color this blue, and I'm going to give this a label. The label is going to be the equation that this corresponds to. This is y equal to 3, right? This is a label for it. I'm going to color this, say, red, and I'm going to label this x equal to 5. Okay, so that once I do this, I have been asked to add a legend here, right? A legend is nothing but something that denotes the correspondence between the color of the graph, the color of the curve, and the equation or label corresponding to it. So that's why I added this label. So if you add a legend, it will automatically do this for you.
Sir, by default, it gave orange color. Yeah.
By
Earlier.
Can you repeat the question?
I said, sir, did it give the earlier color by default? Because I think before changing the color, maybe I think I missed that part.
Yeah. By default, it gives a different color. If you use that function plot the second time, it will give you a different color for that curve. But yeah, that what we have done here is we have enforced this by giving specific colors to each of these curves. Okay, so that's how you add a legend. Yeah. Yeah, go on. Any other questions? Yeah. Someone is trying to ask.
Sir, instead of 50, we could have written 2 also.
Instead of 50, yes, in this case it will work because it's only lines, right? So in this case it would have worked, but yeah, you are right. So we can maybe just have 2 points. So 1 second. Okay, and it would have where I change this to, yeah, this also changed, right? So yes, you are right. So in this case it works, but let's say you are plotting something which is not a line, then you have to be careful. All right.
What is this PLT dot legend?
Legend, this one.
Legend is okay. So in case I don't explicitly write PLT dot legend, it won't take label.
No, it won't give you the legend.
Okay.
Okay, so is this fine with everyone? Can I move on?
How does the
Yes, sir.
legend figure out the graph color?
Sorry, how to?
How does the legend figure out the corresponding graph?
Using the label, right? So we are associating this graph, this curve with the label y equal to 3. So that will.
Got it. Yeah.
Okay,
Sir,
so now
what is the significance of that comma 2 and comma 50 that you did? So,
so in this, it doesn't. So what we are doing is we are plotting y equal to 3, right? How you just, since it's a line, you just need 2 points to plot a line. You just need the starting point and ending point. So that's why if you just give 2 points, if you divide the interval 0 to 6 into 2 points, namely 0, 0 and 6, right? If you do that, it's enough. You can plot a line because only 2 points are required to draw a line segment, right? So if you just changing it to 50 is unnecessary here, but if you have to plot, say something like, I don't know, y equal to, say, let's just temporarily comment this out. So maybe I am plotting y equal to x square and let's say x equal to and y equal to something else, right? So I don't know, minus x square. This may not come out properly, but yeah. So you can't do this using just 2 points, right? So you'll have to, yeah, I have to uncomment this. So yeah, I hope you got the point, right? So if you're plotting things like parabolas or something more complex, say logarithm function, things like that, you can't just do it using 2 points, but you're plotting a line here, so it works.
okay. So if you don't mention anything, is there any default value that it takes? Or
Yeah,
like,
50.
okay. Okay. Thank you.
Okay, so
Sir, if you don't mention, it will be continuous.
it will appear continuous because there are like 50 points, right? So
So can you scroll up a little bit? Just to the previous, yeah. Thank you, sir.
yeah, so now we come to the final part in this collab. It's called a subplot, right? So, yeah.
Just a second. So before going ahead, I just plotted on the basis of x is equal to linspace 0, 6 with 50 spaces. Y is equal to np dot ones multiplied by 3 means the one number of array of 3. Then on the second graph, np dot linspace of 0, 6, 50, and x is equal to y to raised to power 2. So the first plot is stopped at 5 itself, and it is not plotting till 50. Why it's the case? I'm sorry, it stopped till 6 only, but the x to the power y square is getting plot to the extent of 35 and 36 for all the spaces. Okay, I'm so sorry. I got my answer. I'm so sorry.
Okay.
We can move ahead. So sorry.
Yeah. Okay, so sometimes we have to plot multiple. So we'll have to plot multiple plots in the same window. So one use case is in machine learning is when you have to plot the training and test loss, or rather the training loss and validation loss, right? So you'll have one window where you want to plot the training loss and another subplot, right? So we call these subplots. So you want to compare the training loss and validation loss, or maybe usually you do that on the same plot. So a better example could be, yeah, I think that is a reasonably good example. Maybe you want to plot, there are certain curves called ROC and AUC curves. You learn that in machine learning practices. So there are few other metrics that are used to tell you how good the classifier is doing. So you may want to plot all of these in a single window, right? So how do you do that? That's where the idea of a subplot comes in. So we are going to plot 4 functions here. So the first one is ln x, right? So this is log of x, as we know. The second one is e power x, so that is exp of x. The next one is sine of x. You have a function predefined, and next one is 1 by x. Okay, so each one we are going to plot. So we are going to choose the line space according to the ones given here. So the first function requires a line space of 1 over np dot e square, comma e cube. Okay, let's use the same 50 default. And we'll end up plotting this. So this plt dot plot x comma y. Now this has to occupy the, I have a graph for this. Okay, this has to occupy the top left corner, right? So if you want to plot 4 subplots, this is how you do it. So the first argument and second argument gives you the number of rows and number of columns into which your window is going to be divided into. So my window is going to be divided into 4 parts, namely 2 cross 2. Okay, and the third argument is going to give you the index of the window. Which window is this plot going to appear in? So 2 means it will appear in the top right, second row, second column. 3 means bottom left, right? So it goes row wise. So 1, 2, 3, 4. Okay, so we are going to do plt dot subplot of 2, 2, 1. So that is the leftmost window. We are going to plot this. Okay, this is plot 1. And we are going to title this. So it's going to be a complete plot. What is this? This is y equal to ln x. For now, let's just comment these out. Okay, let's first look at this and see what happens. Okay, so what has happened? Sorry, I didn't plot this at all. Plt dot plot x comma y, right? So okay, that is ln x.
Sir, why did we use 2, 2 only in subplot?
2, 2, because you're dividing your plot into 4 parts, right? So 2 cross 2, 2 rows and 2 columns.
Okay.
That's why the 2s are there here.
So when you are plotting x comma y, where is the y you have defined?
Sorry, can you repeat the question?
Sir, where? Okay, plot.
Okay.
Y you have defined as ln x, right?
Y is ln x, yeah. Yeah, this y I have not explicitly defined it. Yeah, you could define it explicitly if that is more, that will add to the clarity. Then this is y, right? In this case. Okay, now the second subplot, I will delete this part, right? So this is plt dot subplot 2, 2, 2, right? Second subplot. X is going to be from 0 to 3, simple here. And we are going to plot e power x, right? So we are going to plot e power x. So this is np dot e. Could do something like this, but there's a function called x. This is nothing but e power something, right? So e power x. Plot x comma y and give it the title y equal to e power x. So there is some of you know LaTeX. If you use this $, then that e power x will get rendered properly. So if you remove this $, that the rendering will be poor. But that's not very important from a basic understanding point of view, right? So
earlier you didn't define y, but it was taking it correctly. How it is so?
Because I had directly plugged in this here.
Okay, got it. Yeah, sorry.
Okay, so that is plot number 2. Plot 3 is again plt dot. Now it's just repetitive, right? So 2, 2, 3. That's the third subplot, and it's from 0 to 2 pi, right? So x goes from 0, 2 pi, 50 points, right? So this is 2 dot np dot pi, right? As we discussed earlier, np dot pi is pi, and you plot x comma y. So where y is np dot sin x, sin of x, okay? And you give it the title y equal to sin x. And I'll plot the fourth one directly. So it is also it's from 0 to 5. Okay, so this is where you have to be slightly careful. So this is from 0 to 5. So this is where, as someone was mentioning, if we can ignore the start point, it will be very useful. Okay, but unfortunately, the endpoint can only be optionally excluded. You can't exclude the start point. That's what I see here.
Sir, why will it be useful if we ignore the start point here?
For this particular case, can you tell me why we are trying to plot 1 by x?
Oh, okay.
1 by 0
will be infinity.
Yes, sir.
Yeah, right.
Defined.
Yeah, one way to get around that. So in fact, this will work. The NumPy will throw a warning. So if you notice, if you define 1 by x and you try to plot x comma y and give it the title plt dot title y equal to 1 over x, and try to plot this, we are missing the subplot, right? So plt dot subplot 2 comma 2 comma 4, right? That's the final subplot. So note that it gives you a warning. So runtime warning divide by 0. It's not an error as yet. But then it's just to be safe, we can do something like start from 0.001, maybe 0.1 instead of 0, right? So that gives you a better looking curve, and the warning is also suppressed. Okay, so we have plotted all of them. So one trick to expand the size. So currently the subplots are all they are jammed together and you're not able to separate them. So there's something called RC params, right? This is a configuration. It's a dictionary for the plotting facility where several parameters are set, right? So there is one parameter called fixed size. It's the size of the figure. You can increase it, right? So by default, I don't know what it is, but 8 cross 8 will make it bigger. Okay, so if you make it bigger, then that's one way to clean your plot, right? So this plot looks much cleaner. All right, is the idea of subplots clear to all of you?
Like I'm confused, sir.
So can you explain the last parameter, the RC dot parameter one?
Yeah, so this is actually a dictionary, right? So if you look at RC dot params, you will see that there are several, these are configurations. So this is configuration parameters, right? So there are so many configurations possible here, right? So there are some configs for axis, for defining the axis, for defining the font, right? So for defining font size. So if you, for example, if you change the font size, your font dot size, right? So I'll just show you what happens if you change the font size to, let's say, font dot size. If I make it 20 and run this, note that the font has changed, right? So you get huge sizes for the title and for these are called the ticks, right? X ticks and Y ticks. So that's one way of.
So we can do it by putting the same with a comma in that plt dot title.
PLT dot title, yeah. So I think that also works. But this is some kind of a global parameter, right? So you can globally change the whole thing, but you're right. So there is font size that can be passed as argument there.
Otherwise, we have to repeat it every time.
You're right, yeah.
Got it.
Okay, shall I move on to the next collab or?
So it is a dictionary.
Yeah, it's a dictionary, yeah.
Just one question. In the beginning, you said, what's so important about this subplot? I mean, we can still have 4 different plots, right? So,
right. So you are right. So sometimes what happens is for the sake of presentation, right? So you might want to group together certain plots in the same window, right? In order to give a more coherent presentation. So instead of having it as 4 separate plots, if you can compare 2 plots side by side, for example.
Okay, thanks.
One more question, sir. Is the plt dot subplot and after that the 2 comma 2 is mandatory, or we can change it as well?
That you can change. For example, if you want to change this to a sequence of a line of one single line, right? So you could have something like 4 comma 1, right? So this whole thing will.
So it's more like rows and columns.
Correct, exactly. These are rows and columns, right? So this will all appear on one column, right? So this will be four rows rather, right? 4 rows, 1 column, but the whole thing will be in the first column, right? So this is your choice. What to do?
Sir, also, is there a way to copy these plots properly and paste it outside this collab?
Yes, you
Yeah.
can.
So you can, there's certainly a way to do it in, so one thing you
Like
could,
actually in my editor, I can just see a copy button
right,
straight
so
away.
one thing you could do is you could do save fig, right? So you could save this figure as fig1 dot say png, right? So if you run this, this will get saved here, right? So this will get saved here. You can go and look at folders, right? So
Yeah, it comes in the folder.
right, so this you can download.
Okay, sir. Thank you, sir.
Okay, so going back to, yeah, so I think we can leave this collab now.
So the 2 we should write it uniformly, right? In all the subplot.
2 yeah, 2 you have to write, yeah, yes, that's it.
No, we cannot change for one sub.
No, right, that will not be the right thing to do, right? Because it will get, otherwise you'll get confused where to plot what. So for example, if I change this to 3, for example, okay, so auto removal of, so it complains, right? It should, I don't know if it really works.
Sir, excuse me, sir.
Yeah.
Sir, we can make 3, 3 and subplot.
You can, provided you have
Yes, sir.
9 or maybe say 8 plots.
Yeah, sir. Yes, sir. Yeah, sir. Yeah. Then
So
index will be 1, 2, 3, and 5.
Right.
Like that. Yes, sir.
If we create more, if we declare like more, but we add less of subplot, will that work?
Yes, it will work. Only thing is that it will be empty. So for example, if you make
Okay.
2, 3 here, right? So and you start plotting them, you'll have extra space. You'll have space for 6 plots, and 2 of them will be empty.
Okay.
Sir, what if I want 3 plots to be in one first row and only 1 plot in the second row? What can I do?
Then you can do something like 4 cross 2, and so not 4 cross 2, 2 cross 3, right? So you'll end up with 6 graphs, 3 on the first, 1 on the second, and 2 will be empty on the.
Sir, I don't want it to be empty. I want it to be in center.
Okay, then I believe you can do 2, 3 and then 5, right? So something like that. So say 2, 3, 2, 3, 2, 3, 2, 3, and instead of this being 4, if you make it 5, something like this. Is this what you're saying?
No, sir, I was saying it should stretch from left to right. It should.
Oh, then it's better if you make it a separate plot, right? So you can maybe create a new window and plot it, right? So that's the use case that I currently don't know how to do. You check it using.
So is it possible to make subplots inside subplots? Like in the second row, if we make one subplot and fill it from start to end.
I am sorry, I didn't get the question.
Possible to make subplots inside a subplot?
Is it possible to make subplots? That's the only part I am able to hear. After that, I am losing.
Like the guy is asking 3 plot in one row and 1 plot in second row. Totally stretched.
Okay, right. Currently, I don't know how to do that, but I'm sure it's one search away, right? If you just search it on Stack Overflow or our GPT, both of them will be able to help you. Okay, so I'm only, as I said, I'm only having the essentials with me right now. The rest you can do a search. Okay, so we'll have to move on because it's just like very important. Matrices are important, and then we have NumPy arrays also. Okay, so we have already looked at okay. Yeah, there were too many sessions running, so I've just closed some of them. Where is this? Yeah, so NumPy matrices. So this we'll just quickly go through. Okay, so how do you define a matrix? So very simple. So just go for a list of lists. Just like what you do in Python, right? So that's all there is to a matrix. Instead of just a single list, which we did for a vector, this is a list of lists. Okay, so how do you add two matrices? It's very simple again. So you define one matrix and you define another matrix 5, 6, 7, 8. Okay, so C equal to A plus B. Again, the translation from NumPy to Python is very straightforward. Okay, scaling a matrix, again 3 star n. I'm not doing this, it's very simple. So this is A star B. Okay, again, I'm leaving it. The solutions are already there, so it's really
Sir,
simple.
please show the addition again now.
Sorry?
Addition part. Addition, please show again.
Yeah, just A plus B.
But I am getting error.
You must have defined it. The definition should have been wrong in either A or B.
Actually, what I did.
double brackets?
Okay. I didn't use the double. Sorry. Got it.
Okay, so this is element wise is just A star B, and maybe this part I'll tell you because so don't think that I'm going fast. It's actually very simple. So you can figure this out yourself. So you want to apply this absolute value on each of these elements. So there is one function for that in NumPy. It's called np.abs, right? Absolute value. If you apply that on A, you will end up with this being applied element wise. Okay, so you want to square each element of a matrix. So you have this matrix given by 1 comma square root of 2. So there is again, if you could either do 2 power 0.5, 3 power 0.5 comma 2. And then if you try to square A element wise, this is what you do. Square root of 2 can also be written as np.sqrt of 2. And root 3 can be written as np.sqrt of 3, right? So we again just variations, the same idea. Okay, so all these are straightforward. Now here we come to something that's slightly not so straightforward. So once you have a matrix, okay, so once you have a matrix like this, there are two ways to get a transpose, right? One is np.transpose. Okay, so if you do np.transpose, that will give you the transpose. This is one way of doing it. Alternatively,
shape also will change, na, sir?
Which one? Yeah, shape
Once
also.
Yeah, right.
Right. The other way and simpler way is just m dot capital T. Okay, m dot capital T will give you the transpose. Very similar to the m superscript T that we use for the matrix transpose in mathematics. The NumPy equivalent is m dot capital T. Okay, so this is better than np dot transpose, simply because it makes your code more readable. Okay, you clearly see what's happening, and this transition from math to Python is smoother here.
Sir, why are you writing that functions are better, like in time complexity?
No, not from the time complexity point of view, but from readability.
Okay.
Yeah. Okay, so I think m dot t internally is going to do something like this, right? So okay, now we come to the shape and dimension. So recall that vectors had this idea called shape, which was nothing but the number of elements. Now the shape of a matrix is going to be the mathematical dimension that we are used to. So this is a 2 cross 3 matrix. So the shape of this matrix will be 2 comma 3. Okay, it's a tuple. The first element of the tuple will be the number of rows. Second element will be the number of columns. Okay, so this is what we call the shape. And what is called the dimension of a matrix. The numpy dimension is in this case 2. Okay, as I said before, if you want to write down a matrix, you need to have 2 dimensions. You need to go horizontally, you have to add elements on rows, and also you need to go vertically, right, on columns. So there are 2 dimensions involved. That is what we mean by numpy dimension. Okay, so matrices are 2-dimensional numpy arrays. Vectors are single-dimensional numpy arrays. So this is something you need to be very clear about.
So numpy dimension is because of the rows.
Yeah, how you write it down, right? If you think of it, how do you write down a vector as opposed to a matrix? So vector, you just write it down in a single line, right? A single dimension is all it takes. So you can also think of this as indexing. How will you index? You'll start from 0 all the way up to number of components, right? So it goes in.
It is like the number of nested brackets, right?
Yes, you could think of it that way also, right? If you look at it from a Python standpoint, yes, number of nested brackets. But if you think of it from a more visual standpoint, you can write down a vector along a single row or column. But for a matrix, you need to do it spatially, right? So matrix is a grid of numbers, and when you say a grid of numbers, you need 2 dimensions to have a grid has 2 dimensions. It has a width and height, or length and height.
Okay, so it is also possible to make a 3D NP array actually.
Correct. It's right. Yeah.
Okay.
Yeah. You are right.
So the dimension of M transpose would be 3.
Yeah, M transpose. M transpose will also have numpy dimension 2, right? The shape will be different. So remember this. So shape means it deals with the number of elements that are there in your array. Shape deals with the number of elements. Dimension deals with the
length of array.
Yeah, the length of the array, or no, not the length of the array, because if you think of length of the array, that's the shape.
Somebody says like nested loops.
No,
Would be the
like more
dimension.
like length of the array. Na? If you do len of this, it will be same.
Yeah.
No, I didn't say nested loops. I said nested brackets. Like there is for vectors, it was just np.array open square brackets. Like there was one set of square brackets, but for this there are 2 sets of square brackets.
Correct. Yeah, it's
So
either
M transpose would be having 3 sets of brackets, right?
No. And so what is M dot T, right? M dot T is, see, what is M dot capital T? It is the transpose, right? It is 1, 2, 3, 4, 5, 6 in the columns, right? So if that is also a matrix, no? All matrices have numpy dimension 2. See, you have, so when I say n dim, right? N dim refers to, are there rows and columns, or is there only a row or a column?
I guess 3-dimensional matrix will be something like a Rubik's cube.
Exactly. Yeah, you're right. So that's right. So maybe if we come to that, when we come to that, you'll understand whoever asked Ravi or whoever asked the question, maybe you'll understand it better. But for now, just take this, right? So this is what you have to keep in mind. Vectors, when you say vectors, think of them as just rows, right? There's only idea of row. There's no idea of a column. When you think of matrices, think of rows and columns, right? So this is 1-dimensional NP array, right? This is because there are rows and columns. This is a 2-dimensional NP array, and there are higher dimensional objects. So in general, I think they are called tensors. So you can think of the 3-dimensional NumPy array as having a row, a column, and also a depth, right? How deep it is. So that is a 3-dimensional NumPy array. Okay, but mostly we'll be dealing with vectors and matrices, right? So it's either num dimension 1 or NumPy dimension 2. Okay, so I hope this distinction is clear between shape and dimension.
Yes, sir. Clear, sir.
Okay, so vectors can also be viewed as matrices. So we are already familiar with this part, right? So if you have a column vector, so this is a column vector, right? So 1, 2, 3. you can also treat this as a matrix, right? So if you have to treat this as a row vector, what will you do?
Transpose.
Okay, so this is a vector, right? It has only one dimension. You have to change this into something that has two dimensions. So if you want D cross 1, or let's say in this case, you want to make this a 3 cross 1 matrix.
You can
How will
add a set of square brackets outside this.
Okay, so
we have to keep
Okay, so
every
1
element
will be its
that
own
square
row,
bracket.
2 will be its own row, and 3 will be its own row.
Okay, right? So you have to make each of them. Okay, so there are, if this is 3 cross 1, there are 3 rows, right? So now if you look at X dot shape, it will look like a matrix. So it will look like a 3 cross 1 matrix. Right? You could also do this as a column vector, right? So sorry, this is a column vector. You could do this, treat this as a row vector. How will you do that?
Just we have to add the brackets, nothing else.
Right. So you just need to enclose it with.
But X dot shape, what it happens, sir? It didn't give in anything, right?
No, I didn't print it, right? So as I said, only the last line will get printed, right? So now if you notice, it will be 3 cross 1, and this will be 1 cross 3. Okay, so you will see some of them use this convention for vectors, but personally I think much easier to treat vectors as single dimensional arrays, because you just need one dimension to write a vector. Okay, so don't.
So can you do?
Yeah.
So can you do the x dot dim for both?
Yeah, x dot dim for both. Yeah. So.
Dot and dim.
No, sorry. Yeah. X dot end dim. So both are two-dimensional because of the way we have defined them here. But I would strongly recommend you to not represent vectors as matrices, at least in NumPy, right? So in NumPy, it's better to just treat them as single-dimensional NumPy arrays. That makes life easier. Is this fine regarding shape and ending?
So if possible, if you can just give a brief again, because this is confusing topic.
Yeah, so this what you can do is, can you just go back and watch this part alone, because I would like to cover few more aspects before we close.
How did you tell to define vectors?
Vectors are single dimensional NumPy arrays, right? As we have been doing so far. NP dot array of the list of numbers.
So we should define it as a single dimensional.
Yeah, always.
Means we don't have to do it in a matrix way. We have to do it in a single dimensional way.
Yeah, that is better is what I'm saying.
Oh.
Sir, if it is useful, can you please explain the dot reshape function also here?
Yeah, I'll come to that, right? So it has a place. I'll finish this and come back.
Okay.
Okay, so these are 4 products that you will see, right? In various aspects of ML, you will see 4 products come up. So one is obviously matrix multiplication, right? So let's quickly do that. So 1, 2, 3, 4, 5, 6 is 1, and 6, 7 is 8, 9. Okay, so C is A into B. So if you recall, I was mentioning that A at B gives you the product. It gave the dot product then, but now it's going to give you the matrix product. Okay, so remember that A star B is wrong. A star B will give you element-wise product. In fact, it will throw an error if you do A star B, because these are 2 different dimensions, right? So you can't multiply 2 cross 3, 3 cross 2 matrix is element-wise. You can only do matrix multiplication. So A at B will give you the matrix product. Okay. Now Now next one is matrix vector product. Okay, matrix, if you want to multiply it with a vector on the right hand side, you need a column vector. Okay, you can't multiply a matrix and a row vector on the right. Okay, it has to be a column vector. So let's take this matrix and the vector x. Okay, so interesting part about this is the beauty of NumPy is that this also can be computed just using at. Okay, NumPy, what it will do is internally what it will do is it will turn x into a column vector, multiply a with the column vector, and then when it produces the output, it will convert it back into a single dimensional NumPy array. Okay, so I'll just repeat this. What it does is for matrix multiplication to work, right? Matrix into vector, the dimension of the vector should the shape of the vector, right? So how many components should the vector have? It should have as many columns, right, as the matrix. So that is the first point, right? So this has 3 columns, this will have 3 components, right? What it will then do is it will convert x into a 3 cross 1 matrix. It will multiply these 2 matrices, right? A 3 cross 3 matrix and a 3 cross 1 matrix can be multiplied. You will end up with a 3 cross 1 matrix. So ideally your output should be a matrix, 3 cross 1 matrix, 2-dimensional NumPy array should be your output. But what you see here is a 1-dimensional NumPy array, which is a vector. This is something NumPy will do internally. Okay, is this part fine?
Sir, NumPy will always store a vector as a row vector, right?
So in a sense, it treats it as a row. We could say it treats it as a row vector, but then it's a bit tricky, right? You will see that in the next example, it does something different.
So if you want the matrix output, you should give x as matrix then.
Can you repeat the question? I was not able to get the question. The matrix. Hello?
Sorry, I was on mute. Yeah, so the output is, what do we say? Vector it is, right? Say
Yeah.
if you want the output as matrix, you should pass x as a matrix.
Correct.
In that case, okay.
Yeah, in that case, it will remain a matrix, right? The output will remain a matrix, but here, what you get is a vector. Because, well, if you think about it, right, the matrix vector multiplication results in a vector. So NumPy does just that. It gives you back only a vector. Okay, so you would have guessed what will happen here also. So here, you can, if you want to pre-multiply a matrix, you can only do that using a row vector, right? You can't multiply a column vector into a matrix. That will not work. So you have to, it has to be X transpose A. So we'll copy this part. Remains the same. A and X are the same, but instead of doing AX, you are going to do X transpose A. Okay, as you might have guessed, here also it works, right? Just using the at works. Here what it will do is it will convert X into a 1 cross 3 matrix. It will multiply it with A. The result will be a 1 cross 3 matrix again, right? But then NumPy will convert it into a single dimensional NumPy array like this.
So, but what will happen if we do x dot transpose at the rate A?
There is no X dot transpose, right? So that is another point. So for a vector, there is no transpose, or rather, the transpose of a vector is the vector itself. There's no notion of transpose for a NumPy vector or a NumPy 1D NumPy array. Because there are no 2 dimensions involved, right? There is only 1 dimension. So there is no transpose as such. Or rather, the transpose is itself. Okay, Okay, so this
based on the situation, it will consider it as row or column vector.
exactly, yeah. So this that depending on what the operands are left and right, it'll do this business of treating it as a row vector or a column vector. So the endpoint, the upshot of all this is that no matter what multiplication you are doing, whether it is matrix, vector, vector, matrix, whatever it is, just using something at something works. Okay, so final part. So this we already saw, right? Dot product. So dot product also, it will do this business of conversion appropriately, right? So it will change x into a row vector, y into a column vector. That's why x transpose y is also x at y. Okay, if you followed whatever I mentioned so far, x will become row, y will become column vector. Therefore, x at y works. It's a matrix multiplication again.
So basically, it adapts accordingly.
Yeah. Okay, so one product which is totally different from all of them that we have seen.
Sir, for vector multiplication, we can't we use dot here? I mean star.
Where?
Sir, x and y, where x and y are vectors.
Here, right?
Yeah.
In the dot product, yes, you can use. Yeah, np dot x comma y works, but then this is more of a common. So since ACT is working for everything before,
okay,
we can just as well use it here.
Okay.
Okay, the final product is the outer product. So where have you seen outer products in the MLT course?
Covariance matrix.
Exactly, right? So you saw it in the covariance matrix. So that is where it comes in. So here what we have to do is there's a nice utility called np.outer. So let's define right. So np.outer of x comma y can compute the outer product for you. It will do xy transpose and give you the answer. So just want to mention that x at y transpose will not work. Okay, this will end up computing the inner product or dot product. Again, we call that y as a vector doesn't have a transpose. The single dimensional array in NumPy doesn't have a transpose. It is just itself.
Sir, what is the difference between inner and outer? I mean,
yeah, inner product is x trans. So one kind of inner product is x dot product, right? So dot product is x transpose y. The outer product is x y transpose. So the first one will give you a scalar value. Second one will give you a matrix.
Sir, is it outer is something like cross product?
Well, I'm not sure if you can call it. It's not the cross product because cross product that I remember is that will also give you a vector, right? The cross product. It's not the cross product. It is the outer product. I don't know to define it.
Yes, sir, it is cross product, but we are using outer as by using at the rate, it will calculate the dot product. So just to get rid of the dot product, we are using outer. It's same as cross product.
I don't remember. So the cross product that I studied in physics was different. It was the cross product between two vectors used to be a vector. The dot product used to be a scalar, cross product used to be a vector, not a matrix.
yeah, that we know, sir, but here it is, I don't know, sir, what is this?
Yeah, so outer product is xy transpose, right? So that part I hope is clear.
Okay, sir.
Okay, so just as we had matrix vector of zeros, you can have a matrix of zeros. You just need to define shape, right? So you want a 2 cross 4 matrix of zeros. So let's define the shape of
10 o'clock.
the matrix, right? So this is how you get a matrix of zeros, matrix of ones. So here you want 3 cross 2 matrix. So put that in. So no change here. So there's a nice function for identity matrix. So there's something called I. Okay, I for capital I. So given it a fancy name here. So if you just plug in the order of the matrix, that will give you an identity matrix of whatever order you want, right? So 5 cross 5, just put in 5. Diagonal matrices are again quite useful. So just plug in the diagonal entries. That will give you a diagonal matrix, np.diag. Okay, so this is a diagonal matrix. Next we come to indexing and slicing. Okay, very important because you need to get hold of certain indices, right? So for example, if you have a data matrix of shape d cross n, and you want to get hold of the, say, 10th data point, you want to get hold of all features of the 10th data point, you must know how to slice a matrix. Or if you want to get hold of, let's say, the third feature for all the data points, right? You need to get a particular row of a matrix, right? So slicing and indexing are important. So we'll discuss this part. Okay, so here I have to let me introduce one function just to make life simpler. So recall that we were discussing this idea of np.a range, right? So a range from 1 to 11 will give you this vector from or one-dimensional array from 1 to 10. So what you can do to get a matrix like this is you can reshape this. There's a function called reshape. Okay, so if you call this V and you want to convert this into a 5 cross 2 matrix, you just need to enter the dimensions that will reshape the matrix, the vector, and give it to you in this. Okay, so these 10 numbers have been shaped into a 5 cross 2 matrix. This fine. What reshape is?
Yes, sir. Here if you give a reshape as say 10 comma 3, then will the other elements be 0?
No. So you have to give it. So yeah, it should be compatible, right? So the shape should be compatible. If it's not, it will say that you can't reshape an array of size 10 into 10. Right? So that
What if less?
Dimension should match.
And so there is a we can, if we want the number of columns to be fixed, and we don't know how much rows it will cover, then how it will do?
Yeah. So there is a way to so there is if you set the argument to -1, what it will do is it will automatically figure out that the missing argument is 5. So you only know the columns, let's say. This will usually work for things like higher dimensional arrays where there are 3-4 dimensions involved, and you know 3 of them, and fourth one you don't know. So if you plug in -1, this will figure out that it'll do the division internally, right? 10 by 2 it will do, and
Sir, can you do -1 comma 3? It will throw an error, right?
Yeah, that will be an error. Yeah.
Okay.
Okay, so
-1 automatically computes the number of rows required.
Rows or columns, depending on where you place the -1.
Oh, okay, got it.
Okay, but there can be only one -1. If you have two -1, then it will again be a problem because.
Okay, because there are infinite possible combinations.
Yeah.
Okay.
Okay, so now what I'm going to do is I'm going to just what do you call this function? One function. Yeah, I'm going to compose two operations, right? So I'm going to first get hold of a range of 10 numbers, and then I'm going to reshape them into. So I'm function on top of function, right? So that will give me m. Okay, so I'm going to obtain m from now on. So I have obtained a sequence of 10 numbers, reshaped them into 5 cross 2 matrix. Okay, so this is, we have the function, we have the matrix now. We have to extract the third row of the matrix. Okay, third row is what? This particular row, 5, 6. Okay, so very simple, right? So this is, you think of this as a list of lists now, and there are 5 rows. You need to get the third row, just have the index to be 2, 0 index. Okay, rows are very simple. So I hope that is fine. Now this again, let's take a sequence from 1 to 9 and turn it into a 3 cross 3 matrix. Okay, now I need the second column. Okay, this is where things get slightly complicated. So you have n. Okay, so I have a comma inside. What goes before the comma is the row index. What goes after the comma is the column index. So let's just maybe first look at 1 comma 2. So 1 comma 2 is going to give me the element 6 because it's in second row, third column, right? So 0, 1, 0, 1, 2. Now I need the entire second column, rather. So say I'll maybe write this down in this format. It will be clearer. So m of 0, 1 is the first row, second column. M of 0, 2 is the first, second row, second column, and m of 2, 1 is the third row, second column, right? So this is 2, 5, 8. Is this clear so far? How I extract individually element by element in a column?
Yes, sir.
So
Yes,
what we do now is, instead
Can we
of
put a colon? Like in list, we used to just put a colon.
yeah, that's what we are doing. Yeah. So instead of doing this individually, one element at a time, you know that the column is fixed. Okay, but the rows can be anything. So that you just add a column. A colon. Okay. So that gives you a slice. In this case, the second column, 2, 5, 8. Is this fine? This is how you extract a particular column from a matrix. You fix the dimension of, you fix the index of the column. And since the rows can vary from 0 to end of to the last row, you just place a colon there, indicating that it's entire column.
Sir, here do we have the step size also?
Sorry. Yeah.
Sir, do we have the step size also in this, like in slicing we used to do for list?
I believe we have. So I have never tried it out myself, but I remember someone asking this last term also. I am not too sure. You have to check this, right?
Okay,
But I believe we can, but I'm not too sure.
Okay, sir.
Sir, can we just remove a column from here and see what happens?
Can we remove?
Column. And the 48, I mean, below.
Okay.
Yeah.
That is error, right?
Okay.
So something should be there. So either it's the entire column or particular element in a column, but it can't be empty. Okay, so this this is sub matrix, right? So I want a particular matrix from a bigger matrix. So let's create 1 to 16 and reshape it into 4 cross 4. Okay, that is what this is. What's the mistake?
Range, sir, instead of.
Sir,
Link space. Range. Thank you. Okay, so this is a 4 cross 4 matrix. So we need the slice. Slicing is again very similar to Python slices. So again, before comma, it's row, after comma, it's column. So I'm going to start from the second row, go all the way till the third row. So it means one more than the third row, it should be the ending index. So 0, 1, 2, 3. So 1 colon 3 will be row 2 and row 3. Likewise, I start from the last column, last but 1 or the penultimate column, and go till the end. Okay, this will give me 7, 8, 11, 12. Is this clear?
No, sir.
Okay, so is which part is unclear? Is the first 1 to 3 is it clear? Second row
Yeah,
to
sir. Yeah. So -2.
minus
Sir,
2 is what? Last. So you are indexing the columns from the rows, right? So this -1 is the last column.
yeah,
Minus
sir.
2 is the penultimate or last but one column. So you start from the last but one column and go till the end.
Okay, sir. Okay, sir. Now I understand.
So we could also do 2:4. Will it give the same result?
Yeah, that's the usual, right? Whatever you are used to doing in the case of lists. That is
Okay, sir. Got it.
okay. So that is submatrix slice. Very quickly, so we can do a bunch of things. As I mentioned before, you can do. So if you have a matrix like this, right? Let's take this matrix, and in Max 2, you remember. I think you will remember finding the rank of a matrix laboriously using the row echelon form and all that. So np.lineage.matrix underscore rank will give you the rank of a matrix, right? In this case, this turns out to be a rank 2 matrix. Okay, rank pseudo inverse, right? So this where is pseudo inverse used in MLT? Do you remember?
Yes, sir.
Which topic we use the
Sir,
pseudo inverse?
regression, sir.
Regression, right? So XX
Yeah,
transpose
sir.
XY and all that, right? So normal equations. So if you let's maybe define this. So this is a range of 1 comma, no a range. This has to be an array. So 1, 2, 3, 3, 6, 9. So can someone tell me what will be the rank of this matrix?
1.
This is 1, right? So np.lineage.matrix rank. So this will be rank 1. There is only one linearly independent row, right? So since this is not a square matrix, first of all, this doesn't have an inverse. However, every matrix has a pseudo inverse, right? So this you would remember from MLT. So np.lineage.p inverse. That is all you need to do to get the pseudo inverse. Okay, the pseudo inverse is just obtained using p inverse. So this will be using in tomorrow's collab. So this is useful. Okay, and also important. Finally, eigenvalues, eigenvectors. Where did we use it in MLT?
PCA.
PCA.
Yeah, so PCA, kernel PCA, all of them used eigenvalues, eigenvectors. So mostly we were using symmetric matrices. Therefore, what I'm going to do is I'm going to tell you how to do it for symmetric matrices alone. Easy to figure it out for other kinds of matrices. So there is an np.lineage.hh, right? H stands for Hermitian. So if you remember your MLF topics, Hermitian is the real version of Hermitian is what kind of a matrix?
Real symmetric matrix.
Symmetric matrix.
Yeah, good. So real symmetric matrices are Hermitian matrices. So if you plug in a symmetric matrix, what this will give you is it will give you the eigenvalues and eigenvectors as two values, two return values. So it turns out that the eigenvalues here are -0.2, 4.3, 9.84. If you look at eigenvectors, it will be a matrix, right? There are 3 eigenvectors here, and each column will correspond to one eigenvector. Okay, this is where this slicing will be useful, right? So if you want to get hold of this first eigenvector here, you have to get hold of the first column. So that will be your first eigenvector. Okay, first column. So fix the column index to 0 and let the rows run all through 0 to 3, 0 to 2.
Sir, actually, I don't understand. You've given the two variables eig and eigvec is equal to a single function.
Yeah. So what this function will do is, if you look at the signature, right? So it will return both the eigenvalues and the eigenvectors. So this will return 2 objects.
We are just unfolding 2 tuples.
Okay.
Yeah. It's unpacking the 2 tuple into 2 values. Yeah. So this eigval is eigvec. Okay, and finally SVD, right? SVD is also quite. So there is you can look at this, right? So there is a function to the SVD, and the return is here slightly more involved, right? You have three parts, right? To SPD, singular values, that whatever comes to the left and right. So, okay, so that is regarding matrices. There's a bunch of things. We have only done three. Actually, I wanted to discuss. As usual, I have not been able to cover this.
So we have like 3 more days, no?
Yeah, but we won't be doing only NumPy, right? That's the problem. We'll be doing
It's
NumPy.
okay. We can stay for a little bit longer also.
We
Anyway,
can
it's there on
do
YouTube.
half of the NumPy tomorrow.
Okay, so what I'll do is I'll do some parts which are very important, and maybe till 10:30 I'll do it. So those who want to drop off can drop off.
Anyway, like it is there on YouTube, so we can always come back and watch it if for those who don't have time today.
Yeah. Okay, right. So I'll quickly summarize what we've done for matrices, right? So A plus B, Hadamard B, which is element wise A star B, A B matrix multiplication is A at B, A transpose A dot P. This is the identity matrix, diagonal matrix, zeros and ones, right? Again, I want you to understand the close relationship between math expression and their NumPy expressions, right? So that is okay. So this part is about n-dimensional NumPy arrays, right? So we have seen one-dimensional NumPy array, which is what we have been calling a vector. So this has shape 3 and number of NumPy dimension 1. That's only a row in some sense, right? You only need a row to write this down. This is a matrix, which in NumPy is a two-dimensional array, and there are two aspects, right? Rows, column. You need a grid of numbers to write down a matrix. And naturally, if you extend this, there is, as in Srinivas, someone mentioned, right? A Rubik's cube kind of a structure or a cuboid. It's a
Yes.
dimensional array, right? So this is a row, column, and also a depth, right? So if you think of this, there's 1, 2, 3 on one face, or there are like, you can think of this as 6 blocks, right? 6 blocks, 3 in the front, 3 in the back. So there is like a 2 cross 3 in the front and a 2 cross 3 in the back. So totally there is a 2 cross 2 cross 3 structure. So 1, 2, 3 is written on the front. 7, 8, 9 is written on the 7, 8, 9, 10, 11, 12 is written on the back. So bracket means that is written on the cell or block that is behind this. Okay, so this will look something like this. So let me have a, so this will look something like m equal to np dot array of, so I'll first define 1, 2, 3, 4, 5, 6, right? So this is 1, 2, 3, 4, 5, 6, right? This is your usual matrix. Now, this is one matrix, right? Now, this is itself enclosed within another structure, right? So you have 7, 8, 9, 10, 11, 12. Okay, this is another matrix. Okay, that's behind, that is there behind this. Okay, now if you look at the shape of M, it will be this 2 cross 2 cross 3 structure. Okay, so if I say what is M of 0, what do you think is M of 0 going to be? The matrix in the front.
It will be the first matrix 1, 2, 3, 4, 5, 6.
Yeah, 1, 2, 3, 4, 5, 6. The one that is in the front will be M of 0. M of 1 will be the matrix behind this, which is 7, 8, 9, 10, 11, 12. Okay, visually this is what it looks like. So this is a 3-dimensional array. Okay, so why are we even bothered about arrays if all through MLT course we have only done D cross N data matrix? Okay, features, training data points, that is enough, right? So ideally we should stop there, but that is not true of all data sets, right? What we have studied in MLT is what is called a tabular data set. Okay, where the data can be represented in a table format, table-like format. But in the real world, there are much more complex data sets which are not tabular or structured. They are called unstructured data, right? So images, for example, the image data sets are extremely popular in machine learning and deep learning. Deep learning is like neural networks, right? So study of neural networks, that is deep learning, which you will do in SLT level. So there it's all about images, text data. Okay, these are all unstructured data which cannot be represented as simple tables. So I'll just give you a use case for n-dimensional array. So first one is of course vectors, right? A feature vector is just a single dimensional NumPy array. It's just a vector. There are 100 features here. Okay. The two-dimensional arrays, of course, you have data matrices from MLT, but you can also think of this as an image. So what is an image? Image is just a matrix. Okay, there are like 100 pixels, right, as we call them. So 10 cross 10, there are 100 pixels, and this is called a grayscale image, meaning it's black and white. Okay, so that you can represent using a two-dimensional NumPy array. So images themselves can be represented using multiple color channels, right? So all the color images that you usually look at when you take a pic, they're all, at least some of them can be called RGB images. So there are 3 color channels. So there is a red, green, and blue, and some combination of red, green, and blue is the colors that you see on your screen. So that image can be represented as a 3-dimensional array. Notice that there is 3 popping out here. One dimension for, or rather, sorry, not dimension. There is like one block for each color channel. So red gets one 10 cross 10, green gets one 10 cross 10, and blue gets another 10 cross 10. Okay, so this is a 3-dimensional array. Now we can extend this. In the real world, this is not enough. What if you are dealing with lots of images, right? Any machine learning problem on images will have multiple images, right? So in that case, you need to store these images using a 4-dimensional NumPy array, where 50 gives you the number of images. So there are 50 RGB images. Okay, you can extend this even one more dimension. You can go forward and you can define what is called a 5-dimensional NumPy array to store videos. Okay, what are videos? Videos are nothing but videos are nothing but lots of images. Okay, each image is called a frame in a video. So if you have 50 frames in a video, and if each frame in a video is a color image of size 10 cross 10, that will make it 100 cross 50 cross 3 cross 10 cross 10. So this is actually being used, right? So NumPy arrays, if you were asked to store a video in a NumPy array, this is how you would do it. Okay, so these are generalizations of what we have been discussing so far. All right, so roughly, if you have understood this, it's fine. Reshape we have seen. There are some use cases of reshape. How many of you are familiar with MNIST images? MNIST dataset. Anyone here?
With what, sir?
MNIST, MNIST. Okay, so that will come in ML maybe. So we have not seen that. So okay, so this use case.
Is that the one with many faces?
Not the eigenface, right? That is the eigenface one. This is a different. So yeah, maybe the eigenface also works. So for example, if you in week 2 we did eigenfaces, right? So the faces that. So assume that there are 10,000 faces, and each face is represented by a image of size 784. What you can do is, one use case of the reshape function is to turn the 784 pixels into an image, right? That will be a 28 cross 28 image. So what you're doing is you're reshaping this table into a 3-dimensional NumPy array. This is one concrete use case of real life use case of reshape. Okay, this becomes 10,000 images. If you have to picture this as a stack of images. There are 10,000 images. All right, so this is a tabular representation of the same thing, what I show on the right. On the left, it is a different representation.
So we write matrix as a vector.
We are writing down a matrix as a three-dimensional object. Okay, here we have a matrix. It's a tabular data structure. What we have on the left is volume, more three-dimensional data structure.
So we are actually like cutting squares from the matrix and putting it one behind each other.
Exactly, yeah. You're taking a strip from the matrix and turning it into a image. It's actually image, right? So if you think about it, your face is an image of shape 28 cross 28. And in order to have tabular ML on it, say PCA on it, we converted it into 784, a linear vector. So you'll learn more about, there's a separate course called computer vision where you will see all this in the degree level, where you can move between a image and its vector representation this way. Okay, anyway, so this is
Sir, what is this -1 in R shape? I didn't understand.
so the -1, if you recall, we mentioned, right? So if you want to reshape, so there are 1000 okay, so there are 1000 into 784. So we
Sir,
can
on the right hand side,
yeah.
sir, right image seems to be flattened version of left hand side. I think
Right. Yeah, you are in a sense, yeah.
deep learning.
Okay, you have 10,000 cross 784, right? So this is the matrix. And what I want to do is I want to convert this into, I want to reshape this into something, comma 28, comma 28. I know, so someone has told me that the 784 is nothing but 28 cross 28 images. Each 784 dimensional vector is nothing but an image of size 28 cross 28. But for some reason,
28
yeah, 28 cross 28 pixels, right? But for some reason, they didn't tell me how many were there. Actually, easy, 10,000 are there, but then for a reason, assume that you don't know that. Then -1, if you add it there, that will automatically compute the shape, right? So let's call this P. If you now look at the shape of P, what it has done is it has figured out that this third dimension is 10,000. Okay, that is
how it is making, sir? -1, we require to remember -1 as 1000. That's all. 10,000.
-1, it is not equating it to 10,000. It is, see, what will you do if you want to find out this dimension? You will multiply 10,000 into 784. You will divide by 28 into 28, right? That is what you will do. NumPy is internally doing that.
Sir, -1 is like a question mark. It is like NumPy will automatically calculate whatever is the remaining.
Correct. Yeah, that is right. Whatever is the missing dimension or missing shape value, that it will compute.
Sir, I have a question here. So, like a real-time thing, like what values will this matrix contain? Suppose as we are defining the shape of it as per the face context, what values it's going to take inside that?
Yeah, typically it will take something between 0 and 255. So each
It's like a color thing.
it is a gray. So if you are just looking at okay, so let me just to give you an example. There's actually a nice example in
Sir, MNIST data set is also containing like this.
yeah. So there is the digits dataset. I don't know.
A scalar not data set.
Okay. Just tell me that. I need to know that.
From a scalar dot data sets, import load digits.
From a scale and this is capital D or small d?
Small, sir, small.
This is also small, is it?
Yeah.
Enter.
Import load digits.
Load
sir.
digits.
Load
underscore digits.
Okay, so load underscore digits is what type of object?
Then just we have to instantiate this.
Okay, so
Parenthesis, sir, after this parenthesis.
okay,
And save it is somewhere or yeah, this is also.
okay, this is a data. So what is the type? What does this have? This has
Sir, if you write the data dot image, it is actually 3-dimensional.
okay, data dot image,
Images.
data dot images. Okay,
Data dot images.
okay, got it. Super. So this is 179. So this is 8 cross 8, right? So let's look at one image, right? So this is the image. Now let's see how it looks like. So there's one command called imshow, right? So that will show you what this digit actually looks like. So let's import PLT.
Sir, Matt, so
Yeah. Okay. Okay. So this is a 0 apparently, right? So this is actually not color. So I think you have to say grayscale. I don't know if it's grayscale or just gray. Okay, let's look at this is plt.imshow. Let's question mark and see what are the
It's cmap dot gray. Cmap is equal to gray if you put like that.
yeah, cmap equal to gray. Nice. Okay, so this is how it actually looks. So if you notice, wherever there is a 0, they're all black. Okay, and the values that are non-zero show the intensity of that particular pixel. So the greater the value, the more the intensity. So the closer it will be towards white end of the spectrum. So this is how a typical image will look like. So what I was saying earlier was this reshape, right? So for example, this is now this image will become clear, right? So just forget this, change this into 8 cross 8, and now think of what this reshape is. Okay, so that will. So what have we covered? We have covered arrays, reshape, vector to matrix, matrix to vector. It's not very hard. Okay, so yeah, this I believe Nitin will do tomorrow. Indexing, there are some advanced indexing techniques alone that I want to cover before maybe signing off. So let's say you have this array here, right? So 0, 1, 2, so this 0 to 7, right? This is the array you have. Now you are interested in retrieving elements that are at the indices 1, 3, and 6. Okay, so you could of course do this as x of 0, x of 3, x of 6. You could do that. You will get whatever is there in that particular index. But NumPy has this facility where you can add arrays themselves or lists themselves as indices, right? So for example, this will give me whatever is there in index 1, 3, and 6. So maybe instead of doing this not very clear, so let me add it as, let me give arbitrary numbers. Okay, so I want whatever is there in index 1, 3, and 6. So what is there at 1 is 0. And then at index 3, 3 is there. At 6, 1 is there, right? So what we have done is, we have added another array, right? So this can itself be an array, right? So an array or a list itself can be something that you index into. Okay, so this is advanced indexing. Is this clear?
Yes, sir.
Right. So this is one. The most useful, however, is what is called Boolean indexing, right? So for this, I just want you to look at this particular array, 310 minus 4 minus 215, and I want to just look at. Maybe I'll just change this to 5, change that to 5. Okay. So I want to find out what all elements in the array are equal to 5. Okay, I just do x double equal to 5. What I end up with is called the Boolean it's a Boolean array, right? So list of Boolean values. Wherever the element is equal to 5, that it is true, right? That particular value is true. Rest of them are false. Okay, so this is now. If you want to extract all those elements which are equal to 5, right? You can plug this inside the array itself. Okay, so this is not very clear now, but let me maybe give a, so okay, this asks us to give us the elements which are positive. So let me just say x greater than 0. Okay, so notice that this will again give you a Boolean array with all those elements which are greater than 0. There alone you'll have 2. So what this will give you is this will extract or filter out those values that are positive. Okay, is this clear? How you obtain, how you filter out certain things from your array? This is advanced indexing, and this is where it will be.
We have to use the same variable, right? Like x, and then inside the brackets also we have to use x only greater than 0.
Yeah, because you are, see, this x greater than 0 will give you this Boolean array, and you are using that as an index into x itself.
Okay.
Okay, but yeah, your question is valid. It's not necessary that this has to be x. So there is a use case for that in MLT itself. So let's look at that. Let's say you have a data set that's of this form, right? It's D cross N, right? Two-dimensional, 2 features and say 3 examples. So I'm just randomly adding features here. So this is D cross N. So this is D cross N. Let's print D and N. So there are 2 features, 3 data points. And let's also define the, let's say it's a classification problem, and you have, this is label 1. Second example is label -1. Third one is label 1. Now there might be a situation where you want to extract all data points that belong to the positive class. Right? So this is what we want, all data points that belong to the positive class. So I want all those values where y is double equal to 1. Okay, but I want to index into the original, the data matrix, not the label vector, data matrix. So I want all those examples. So I'm not interested in I'm interested in the columns, right? So this becomes.
Okay, so then we will get 2, 1, -1, -3, and 0,
you will get 2, 1 and 0, 5, right? Because those are the positive examples.
Yeah, 2, 1 and 0, 5. Yeah.
Right? You will get it in this form. Sorry, y was not defined. Y is now defined. 2, 1 and 0, 5. Okay,
So I have a general query over here. Like always, are we going to consider, well, NumPy deals with numbers, but do we have option like we can also give features as some string values or something? Do we apply like that?
Yes, yeah, we do. Yeah, we can give an array of strings. So we'll make use of that in the last day, or maybe even day after tomorrow, where we are doing clustering. We'll give different colors to different points. So there we'll make use of an array of strings.
Okay, sir.
Okay, so this Boolean indexing, this advanced indexing, is it clear? So it's a very useful feature.
Clear, sir.
I think, sir, in the X, we should add one more. I think the shape is 2 cross 1. We should write 2 cross 3. We should write 3 cross 3, I think. Because in the Y, we have 3 cross 1.
So there are 3 examples and 3 labels, right? Corresponding to those 3 examples.
But in the X, we have only 2 examples written here.
No, D cross N, right? So X is D cross N. So 2 features, 3 data points.
Okay.
Okay, so.
Sir, do we use D cross N or N cross D?
For our course, it's D cross N, no? The convention.
Okay.
But usually we write like 3 cross 3.
3 cross 3, no, right? It depends on how many features you have and how many data points you have.
It
N
is
and
n data points, so there are 3 data points. So it is correct only, right?
yeah, 3 data points. So there are 3 columns, right? X is, that's correct, right? So N is 3, no? This is 2 cross 3, D cross N. 2 features, 3 data points.
But usually in machine learning we write three internally we should have 3 list.
3, no, why I don't understand. No, why should we have 3 cross 3?
Because you have written here 3 features.
No, right? There are 2 features. There are only
Like
2.
for the first entry, 2 is feature 1, -1 is feature 2, and 0 is feature
No,
3.
as I told, right? So D cross N, D represents the number of features. There are 2 features and 3 entries.
Oh, okay, sir. But okay.
Okay, so yeah, so there is, you can find out the accuracy based on this, right? So you can, so how do you do this? We'll anyway look at perceptron and all that, right? So we'll do W transpose X and all that. So W transpose X will give you the value, and then whenever it is greater than or equal to 0, so maybe I'll just introduce one particular part. So there is a function called np.var. Okay, so what this does is, you have a condition, and if that condition is true, do something. If that condition is false, do something else. Right? So that is the idea of this. I'll again leave this for someone to do it tomorrow. Sorry, I have to move on few more things before we close. So yeah, the final part which you need to know is the idea of access. Okay, so this is very important. It will keep coming up. I close with this. So you learned about shape, you have learned about dimension, numpy dimension. There is finally what's called an axis. So for a one-dimensional array, there is only one axis. Okay, axis is 0. By default, its axis is equal to 0. For a two-dimensional numpy array or for a matrix, there are 2 axes. The rows, that is axis 0, or the outermost bracket, right? Which, so the nesting, if you remember, you always go row by row and then you go into the columns, right? So the rows correspond to axis 0, columns correspond to axis 1. Okay, and for if you look at this 3-dimensional array, then this depth, the depth thingy will have axis 0, length, the height, the row will correspond to axis 1, and column will be axis 2. So this you don't need to worry, but these two you need to understand. So there are some operations.
Can you navigate to the next slide? Okay. Okay, so it's fine now.
Right, so there are some operations that you can do on an entire axis. For example, here there are 2 row vectors, right? So there is this A, which is np dot a range of 1, 9, and you reshape that into 2, 4. So if you look at A, there is axis 0, axis 1. So you want the sum of the row vectors, meaning row 1 is a row vector, row 2 is another row vector. You want to sum those 2 rows. Okay, so how do you sum across those 2 rows? You can use np.sum, or you can use a.sum. If you just do a.sum, it will give you the entire sum of all the elements in the matrix. But you don't want all the elements to be summed up. You just want to sum along a particular axis. Okay, in this case, we want the axis 0 to disappear, or we are summing along the axis 0, keeping the axis 1 intact, right? Everything along the axis 1 is intact, but then we sum along axis 0. So that you will end up with 5 plus 1, 6 plus 2, 7 plus 3, and 8 plus 4. So one way to understand this is think about this operation as top to bottom. Okay, pressing
Okay,
F.
this is because for matrix axis 0 belongs to columns, right?
Well, axis 0, you can think of that as going down the rows, right? If you go to use this image,
Yes, yes, as it refers to columns, we can say.
yeah, it's a bit tricky, right? You can understand it in the way that suits you the best. Like it varies. So I always get confused. So I refer to this as top to bottom for a matrix. For you're starting from the top row and going all the way down, and you're summing it.
We can think in this way, like first,
So
maybe
if we
when we
put
define a matrix, so we define first row and then column. So row can be considered as 0 and column can be considered as 1.
Exactly, yeah. So the outermost index, outermost list is going across axis 0, and that is the rows. Okay, so the left to
So
right.
if we put x is equal to 1, excuse me, sir. So if we put x is equal to 1, then what will be the answer?
It will be, so that's what we'll do next, right? So it will be the sum of the column vectors, right? So if you do a dot sum of x is equal to 1, you'll end up with 1 plus 2 plus 3 plus 4, because you're going from left to right or along the axis 1. Right? When you go along the axis 1, you're like collapsing that axis, but you're retaining the row in some sense. Right? So you end up with this one. Okay, this is along axis 1. Okay, you could do, it's not just restricted to sum, you can have several operations. For example, if you want to find the mean of the column vectors, so where do we have to do the mean of the column vectors in MLT? Is there any place where we had to find out the mean of the column vectors?
The centering of PCA.
Yeah, in centering
on the data set.
Exactly, right? When we had to center PCA, it was this. We had to do m dot mean of axis equal to 0 or 1. If you want to find out the mean of the column.
0.
Mean of the column. You are going from left to right. See, each column is a point.
1, sir. Axis.
Right? Because you are so if you think of right, so it will be 3 plus 2 plus 1 by 3, which is 2, 5, 8. Right? You want to find out the mean along the columns. So you go along axis 1. Right? Think of this as traveling along axis 1, and every vector you meet, you are adding it and finally dividing it by the number of columns. Okay, so this is mean. Another useful operation that you will do is stacking things, right? So stacking matrices. So let me. So this is one matrix, and B is another one. Right? You want to stack either one on top of the other, which is like top to bottom, A 1, 2, 3, 4, 5, 6, 7, 8. So here you are in some sense doing, you're concatenating or joining two arrays, right? You're joining A and B, but you're doing along axis 0, right? Top to bottom. So the result you get is concatenate. Sorry, it's not A dot concatenate, it's a numpy function. Okay, so this is what you get. You move from top to bottom. You could, instead of going that way, if you go from left to right or along the first axis, you will get them side by side. Okay, so these are two other. Yeah, so this is something I want you all to remember, this axis business. Okay, so that is regarding this. And yeah, final part. So the main point you have to take away from this, from these nearly 3 hours, is that NumPy is math done using Python, right? Where by math I mean linear algebra like mathematics, vector matrix manipulations. So whatever you have learned about these subjects, this particular subject, all that you can do in Python using NumPy. Okay, I think we have to stop here because it's already.
So one thing I want to ask, how far this workshop will help us in our MLP, like I have taken as a theory paper. So how far it will help in that and in the project of MLP?
Well, how far will it help in the case
Will
of
it cover the things of MLP theory, OP and all?
No.
MLP? How will it help you in MLP? Is this what you're asking?
Yeah, sir.
Okay, so unfortunately, what happens is in MLP, the library that you need the most is pandas and not really NumPy.
Okay.
So yeah, it may not. What it will help you in is so sklearn, for example, right? So I'll just give you an example wherever. So if you want to do PCA in MLP, so there is a utility, there's a function called PCA whatever, right? So I don't remember. You just need to use that fit on a particular data set, right? You just need to fit PCA on a particular, it's just a 2 or 3 line function.
Okay.
What this workshop will help you is in understanding how sklearn folks would have actually written that particular function.
Okay.
It's like opening up the sklearn library and seeing and taking a peep inside that. That is all this will do for you. MLP, unfortunately, you need pandas more than NumPy.
Okay. And sir, in MLP project, when we are creating a modeling and all, will this be a base workshop? Will help as a base for it?
No, again, this workshop, to be very honest, it won't help you. It's more of an MLT workshop, right? That's why we call it MLT workshop rather than T workshop.
Okay, sir. Thank
Sir,
you.
It is saying
sir,
no, it won't directly help, but this is, the course is constructed very nicely. MLF, MLT, and MLP.
Sir, I have a
You
question.
take one after the other, it's a real advantage.
Yeah,
If you
yeah.
want
I've
to
done
actually do MLT without MLF, is it possible? Yes, it is possible, but the understanding will not be that great.
No, I've done the same way only. I have
Yeah.
MLP and MLP project in this term. So I was like wondering, will this be helpful or not?
It will be this, like, it's like is alphabet useful for writing poems? Perhaps not.
Right.
So, but
Yes.
still is required.
Yes. Thank you, sir.
Sir,
Okay.
I have a question.
Yeah, go
Sir, do we need to remember all these codes and libraries as when we are going to take the exam, OPP?
OPP is, yeah, OPP, MLT, OPP, you need to remember a lot of things, yeah, unfortunately.
Everything.
Sir, in the MLT OP also we can use that question mark function and check.
That you can use, yeah. Help function you can use, yeah.
Okay,
Sir,
so it will be done
for
on
this,
Google Colab only.
Sorry, two of you are speaking, so I missed out.
yeah, sir, my question was, sir, are we also going to get some sort of practice like we used to get in Python? Practices for practice programming.
There'll be some assignments, but mostly if you practice, if you understand what is covered here, that will be enough to clear the OPP. So this, yeah, OPP don't, I would say, just enjoy it and don't take it too seriously because yeah, it counts towards some placement point, something, but I wouldn't say, don't be too worried about it, right?
Sir, in MLT, in MLT, big zero is already provided all the practice question regarding NumPy, sir.
Yeah, right. So
Yeah.
some questions are there, yeah. Right. Anything else? If not,
Karthik, one request. Would you be able to share this Python book?
This collab, right?
Yeah.
Yeah, so the collab is already there in this tiny.cc. So
And this PDF, sir?
PDF is also there. tiny.cc/MLT_workshop. The solutions are there. So in fact, the solutions are there for some collabs that we didn't do today also. So that is also important. So please go through that. I couldn't do it today, but
Go through which one, sir?
4, right? 4 is important. 4 has more plotting. So for example, it shows you how to, so you can look at it in the solved folder, right? So 4 has, how do you do scatter plots? How do you randomly generate numbers? So this covers all the GMM, EM algorithm, whatever is required for that, right? So sampling is very important, right? So sampling, and how do you sample from distributions? How do you draw bar plots? How do you sample from a Gaussian? And how do you draw a histogram? So how do you do scatter plots, PCA, and PCA on a sample data set, GMM. So this part I couldn't cover today, but the solution is there. So if you have understood what we did today, so see, this is centering and all this, right? So all this you should be clear to you: covariance matrix, eigenvalues, particular eigenvalue, eigenvector, scatter plot. This is axis. Okay, so this is, if you patiently go through it, it's not too hard.
Okay.
One request, Karthik, can you please
Yeah.
tiny link basically in the chat window.
Okay, so this one. May not. I try to copy it, it'll come out a bit. Sorry, it comes out a bit weird. So can someone please type it there? It's. Okay, I have it here. I have it here.
Someone pasted it, I think.
Oh, already? Okay.
Yeah.
Yeah, someone has picked it. Okay,
Sir,
so
sir,
yeah,
when will be our OPP exam, sir?
PP will be on Feb 11th, is what I have been told.
Sir, date, sir, which date?
11th Feb, right? So
okay, sir.
That happens to be a Sunday. Yeah.
Hello, Karthik. Because of work, I joined late. Where the video will be available? I mean, the past videos or something.
So this particular video is currently being streamed, I believe. So let me just check.
I think the email had that, Nandan.
Okay.
The same link, if you scroll down below to the message, there's a YouTube link also.
Okay. Yeah. It's there. Okay. Thank you.
Yeah.
Yeah. So this is that. So this particular, I'm just trying to check. Yeah, it is there. So maybe I can paste that link also here. So if you look at the BS YouTube channel, right? So this under the streaming section, this. Yeah, so this is that. So yeah, maybe I can share the link here. Anything else from anyone?
So do we need to solve some assignments also?
Yeah, we will upload some assignments which you have to solve and submit.
That will be in the regular portal
Okay,
itself.
Yeah, it will be it'll be on the portal. So
Okay.
Is this workshop is directly counted for the placement point?
yeah, some placement marks is there. I am actually not very exactly how many marks, but it is there. Yeah, it is a part of.
Yeah, so like, what is the what is the criteria? Like, we have to just attend this, or is there we have to pass the OPP?
Yeah, you have to pass the OPP, and the marks that you get in the OPP, I believe, will be counted towards some 10 marks, 10%. No, I don't know exactly how they do it, but yeah,
Okay.
that's.
Okay.
Sir, I have not taken the MLT. Can I yet still join this session, sir?
Yes, you can join the sessions, but today it would have been fine because it's more of linear algebra and plotting. But from tomorrow, if you don't know MLT, then it will be tough, right? Because tomorrow we'll do regression, day after tomorrow we'll do clustering,
11 o'clock.
and the last day we'll do support vector machines and all that. So if you're already familiar, then you'll find it.
Okay, sir. Fine. Thank you, sir.
Excuse me, sir.
Yeah.
Sir, are there any chances of exam date
getting changed of like 11th of February there is IIT JAM exam also. So
Oh, okay. I'm not sure. I'll have to check with the team.
yeah,
Yes, sir.
because
Please change it, sir.
even gate exams are happening, I guess. I have my on 10th of February. On 11th, the JAM exams are also happening. So
Yeah, right. That can be changed, I guess. Then we will check. But I can't promise now. I'll have to check with the team and
okay, sir. Thank you, sir.
Thank you, sir.
yeah, thanks everyone. Yeah.
Thank you,
Thank you.
sir. This
Good night.
session will be very helpful, sir.
Yes, sir.
Yes, sir. It was very helpful.
Thank you.
Hello, Karthik.
Yeah.
The video is not accessible. It is showing it is not accessible from YouTube.
I'm able to.
Yes, sir.
Sure. Did you click the link? Because I'm able to.
Oh, sir. No, I'm checking it now. Let me check it again.
It is. Then try again. Okay. Video is not accessible. It is showing it is not accessible from yep.
Yeah.
Which one are you looking at? Because I am.
The one in the email.
Oh, email. I'm not sure. Sorry. This one.
No, maybe you should stop recording because right now it is. I'm able to see what we are speaking over here.